simple type of misery. All these mixed up signals in my head. I still hear these echoes of when you loved me, but now you're just someone in my mind that used to be mine. Baby, your beauty marks. All these mixed up signals in my head. I still hear these echoes of when you loved me, but now you're just someone in my mind. Now you're just someone in my mind that used to be mine.
Called my doctor this morning, I told him these issues, his warnings were just now getting to me. Oh, how could that be? I think I'm stable, willing and able to be consistently willing to please a nice girl to hold me. Oh, why can't that be? I was a rolling the dice until I found you.
Hello. Yes, welcome to day number 3 of our SQA conference in Delft. Okay, this doesn't work, maybe. Okay. Yes, okay, now it works. Good, perfect. Yes, so today I will just welcome you all and briefly mention our program for today. So we will have first a scientific session, then a coffee break, one more scientific session, lunch. Just before lunch, we will again give you a bit of practical information about the workshops. And then in the afternoon, we have a keynote and then session. And at the very end, we will have a dinner in our new church. So exciting. As a reminder, keynote talks are 45 minutes, invited talks 25 minutes, and contributor talks 12 minutes, and we have 3 to 5 minutes of questions. And as always, you can find the information of all the talks on this QR code. And with that, I would like to welcome the chair of the first session, which is Stefan Philipp.
Thanks, Christian. So it's a pleasure for me to host this session. My name is Stefan Philipp, coming from the Technical University of Munich and from the Walter Meissner Institute of the Bavarian Academy of Science, working on superconducting qubits, and I'm happy to see you all around here. I'm also happy that this conference happens, taking out the liberty to already thank Christian for this wonderful organization of this, but I think there will become more of these acknowledgements then later on. And with this, I think we shouldn't lose time, and I would welcome now our first speaker on the stage, which is Morten Kjærgaard from the Niels Bohr Institute, who will tell us about real-time benchmarking and sub-second calibration with state-of-the-art quantum processors. And I'm really looking forward to see what is the progress there and what is the new results. And so, please, stage is yours.
Thank you. Okay, Good. So hello and good morning, everyone. My name is Morten Kjærgaard. I represent the Superconducting Quantum Information Devices Lab at the Center for Quantum Devices and the Novo Nordisk Foundation Quantum Computing Program at the Niels Bohr Institute. So that was a mouthful. Before I get into the talk today, let me just acknowledge also Christian again, and Amber and Eric and everyone who spent time setting up this wonderful conference. It's really cool to see so many companies and researchers and students all hanging out together. It's a real pleasure. So thank you all for putting it on. Okay, so today I will tell you about 2 results from our lab under this unifying title of real-time benchmarking and sub-second calibration on state-of-the-art quantum processors. And so to do that, I would like to just start by considering kind of a cartoon version of a big quantum processor. This is what we hope to build and control. And in particular, what we care about when we look at something like this is really what's going on between the qubits. Okay, we want to build systems that have very high gate fidelities, single qubit gate fidelities, 2 qubit gate fidelities, and obviously readout fidelity as well. Okay. So just kind of at a generic high level, the gate fidelity of either a single qubit or 2 qubit gate, or a multi-qubit gate for that matter, is essentially limited by 2 contributions, an incoherent contribution and a coherent contribution. Okay? And I want to think about each of these separately before we get into the details of what I want to tell you about today. Okay, so the incoherent contribution to first order is basically just the time of your gate divided by T1 or T2, whichever one is limiting. Okay? And I put a proportional sign here. There's some prefactors, but I don't want to care about those. Okay? This is actually excellent work out of Anton's team, and I saw Anton this morning. Thanks for this beautiful equation, Anton and collaborators. Okay, so this gives kind of a simple prescription for what we have to do as a field. Either bring down the gate time or bring up T1. That's how we're going to improve our error rates due to incoherent errors. Okay? Now the gate time in the community has basically not changed a lot over the last 5 to 8 years. It's something like tens of nanoseconds for most of the gates out there, and this number seems to have kind of plateaued. However, T1 has, of course, increased dramatically, continually over the last couple of years, and in fact, yesterday we saw beautiful work on understanding the materials limitations of T1 today. Okay, so that's a good prescription. On the other hand, the coherent errors, they somehow tell you, okay, I was trying to do some gate UG, and I happen to do this other gate U twiddle, okay, and if the 2 are different, that's going to lead to an error. Okay. So the conclusion from this is also straightforward. Okay, control your qubits better. That's what you're going to want to do. Okay, so if we start by looking at this incoherent error, there's a beautiful piece of physics hiding here, although it looks so simple. Because even though T1 has gone up in the community and continues to do so, there's this beautiful piece of physics that's essentially hiding in every single T1 experiment if you just stare at it long enough. So here's an experiment from Anton Potoknik's lab where they made these state-of-the-art qubits fabricated on a foundry-compatible line. Okay. So T1 here is about 100 microseconds, and they measured for about 2 days. And they just saw T1 move around as a function of time. This is not a unique observation. I'll show more of this in just a second. But for now, I just want to emphasize to you that the notion of T1 is a little bit ill-defined, at least in this context. If T1 is moving up and down, then what is your incoherent gate limit error? Okay, not really a well-defined object. Now, for calibration, you can say, okay, just calibrate better. That's just get UG to be better. Now, the problem is it's very time-consuming and requires a lot of physics. Okay, so here's kind of an infamous graph. I love this image. This is from the Google team. It's probably outdated by now, I should say. This is a couple of years old. But each of these nodes here represent a measurement and analysis that they perform in order to optimize a 2-qubit gate with a tunable coupler. Every one of these nodes is a measurement. That's a very daunting task to operate this. Okay. I put in here some typical timescales of these calibration and these T1 jumps, okay? And so I want to start my talk by focusing on this jumpy T1. Okay, so we looked at this data and other data from other teams and thought, okay, there's something interesting going on here. Let's see if we can dig into this piece of physics. So part 1 of my talk will be this real-time decay estimation on millisecond timescales, okay? So here's again the paper from Potoknik's lab. Here's a paper by Shingo Kono when he was at EPFL. Here's a paper from the Chalmers team. Here's a paper from the Google team, and many, many others. And they all show qualitatively the same observation. T1 jumps around in time. Okay? So now, if you stare at this for long enough, okay, and we have done that, it gets a little boring in the end, but what you find is that every single one of these measurements, it looks like T1 is jumping on a scale of roughly minutes. Okay? Then you stare at the data even more, and you see the data is acquired on the same time scale. Okay? So if you're measuring something that's moving around on the same time scale as your measurement, okay, you should probably think we need to measure faster, right? Is there physics hiding underneath this T1 that we just haven't seen yet due to the limitations of how we record this data? That's what I want to tell you about today. So to do that, let me just start with a very simple T1 measurement. Here's some data from a device in our lab. I'll have more to say about this qubit in a second, but this is a roughly 200 microsecond qubit, nothing fancy going on. You can see the error bars here on my measurements. This is essentially just shot noise, okay? So if I now take more measurements, it's going to take longer time. Wall clock is going to increase, but my uncertainty is going to go down, okay? So you can plot a graph like this. This is just a qualitative diagram. This is the wall clock time, how long time did it take to learn T1, and on the y-axis here is the uncertainty of your T1. Clearly that goes down the more data you take. Okay, then you can buy some nice control hardware, maybe you can implement active reset, you can do some better sampling techniques, and you can bring down this curve. Okay? So if you stare at this, you might think, perfect, let's just keep buying better hardware, keep doing more fancy protocols, and basically learn T1 with as little uncertainty as possible, as fast as possible. But there's a really beautiful piece of very, very fundamental physics hiding here. It's called the frequentist limit. You can kind of work this out if you like to do quantum foundations. And what you get is that there's a limit to how fast in wall clock time you can bring down your uncertainty of a T1. Okay? Here's the equation, at least to first order, that shows this in kind of a very idealized situation. Just to give you a sense of what this number is, let's say you can live with a 20% uncertainty on T1. Okay? And you think your T1 is around 100 microseconds. Then you have to execute your entire learning process in 2.5 milliseconds. That's the time you have if you want to hit the ultimate limit of learning T1. Okay? Just to give that in perspective, if you just want a handshake between a piece of control hardware and the computer that's doing the analysis, just sending that network package takes 2 milliseconds over a Wi-Fi. Okay? So in the time of a single network package, you're already far away from this frequentist limit. So you have to do something pretty radical if you want to approach this limit here. Okay, and so we did try to do something pretty radical, and I'll tell you about the experiment that we did. So the idea here is that we're going to offload all of the learning process onto the FPGA. In this case, it's an FPGA embedded on a quantum machine's OPX 1000. Okay? And the idea here is that we're going to run a protocol that has a Bayesian model running on an FPGA, and at every single shot of the experiment, we're going to update our Bayesian estimate of the current T1, and we're going to run that until it converges. That's going to be the protocol. This is work led by Fabrizio Barita when he was a postdoc with us. There's plenty more details than what I'll tell you today, and it's all in the archive posting. Okay, so just one slide on what the theory of this Bayesian updating is, and I want to emphasize the logic that I'll show you will all be executed on the FPGA. Okay? But the idea is we're going to have some prior distribution of expectations. Here's the mean. For technical reasons, we plot the decay rate, not T1. So, okay, just 1 over T1. And we're going to have some initial estimate for T1. Then we have some likelihood functions. If we record a 0, we're going to shift our expectation to the right in this diagram of gammas. If we record a 1, we're going to shift it to the left. Okay? So now we initialize the qubit in 1, we wait some time, and we measure. And let's say that we record a 0. Then the Bayesian model on the FPGA will shift its expectation to the right. This is gamma, so to the right is lower T1. Okay? Conversely, if we recorded a 1, okay, we're going to shift our expectation to the left. We're going to say, actually, at this point in time, the qubit was still in 1. So T1 is going to be longer than we thought. Okay? And we're going to run this process iteratively. So we're going to run it many times. Okay, so here are 2 qubits on a device. These are designed and fabricated by our good friends and collaborators at Chalmers at the Wallenberg Center. So thanks to them for this device. And all the data I'll show today is on this device. Okay, it's a 5-qubit device. I'm just going to focus on these 2 qubits right here. Okay, so here's what the protocol looks like in action. So on the x-axis is iterations of this Bayesian model. On the y-axis on the left is essentially T1, 1 over gamma 1. And on the right is the time that was spent waiting from when the qubit was put into 1 until we measured. Okay, we're going to call that the ith waiting time. And you see something pretty beautiful. You actually see live how the Bayesian model updates its estimate. So the first couple of shots here, blue is 1, red is 0. The first couple of shots, the first couple of waiting times, the qubit is in 1 all the time. So the model says, okay, probably T1 is longer than I think. So I'm going to shift my waiting time for subsequent measurements in order to learn faster. And you see it goes up, and then at some point it starts to hit some zeros, and it adjusts its expectation, and ultimately kind of converges on, okay, if I want to learn as fast as possible for this specific experiment, I should have a waiting time of roughly 100 microseconds. That's basically T1, more or less. Okay? That's what the protocol looks like. In this case, it was 50 iterations. Here in purple, in the shaded area, is the uncertainty of our T1. And in the purple line here is the expected T1. Okay? So you can see that this converges to some value, and in this case, a little bit less than 100 microseconds. Okay, so fine. That was kind of a neat trick on an FPGA. Let's now compare this, what I'll call the adaptive protocol, to a non-adaptive. You could just think a normal T1. Okay? So here again is the data from before, completely standard T1, short noise, boom, 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 evenly spaced data points. Now, if you have an OPX or something else with a fast feedback, you can pretty quickly implement a fast reset protocol. So you measure, and based on that measurement, you either flip or don't flip the qubit, and you keep measuring. If you do that, you get a wall clock time of roughly a second to get this data. So that's already pretty fast, okay, but not as fast as we would like to go. So if we now implement our Bayesian updating model, and we say, okay, run this model until your uncertainty of your estimate of T1 is the same as it was in kind of the slow non-adaptive protocol. That's the challenge we gave the updater here, and this is exactly what happened. So it records a bunch of zeros, a bunch of ones, it has a model shown there, gets the same value out, at least in this specific data set. Okay? What I want to point your attention to is the fact that we spent 8 milliseconds learning the same property of the quantum processor. Let's call it 10 milliseconds, just so it's easy to do the division in my head. That's a 2 orders of magnitude improvement in speed by operating this on the FPGA. Okay? That's a pretty dramatic improvement while learning the same property of the device with the same error bars. Okay, good. So now, just like the other teams, we can start measuring T1 as a function of time. And so that's what we did here. Good, half an hour now in seconds. Basically, we just set the protocol to run, and we go away and drink coffee, and we come back, and we stop the measurement. Okay? There's a lot of data here. In fact, this data set has been downsampled by a factor of 30. Okay, so only every 30th T1 measurement is shown in this plot. If we hadn't done that, it would be like a purple bar going across, so we wouldn't learn anything. In purple is the Bayesian protocol guess, or estimate, I should say. In black is a moving mean, and then in orange is a mean over the entire half hour. Okay, so at this scale, this looks pretty similar to what I showed you in the beginning. Many other teams have observed this like telegraphic noise in T1s. But if we zoom in, something pretty ominous happens. Okay, so here we took essentially a random little slice here. This is now a 4.5 second wall clock time of just observing T1 again and again and again. And I hope you all see the pretty striking thing that we also saw in this data. So let me just walk through with you. So at this point in time, the qubit has a T1 of just shy of 100 microseconds. Okay, nice. You can put that, maybe not in your abstract anymore, but you can put it in the beginning of a paper. We have a good qubit. However, if you just waited 200 milliseconds, the T1 would be half a millisecond. Okay, now that you can put in your abstract. Great. So best T1, half a millisecond. But what we found more interesting about this data is that T1 seems to be intimately linked to how you measure T1. Okay, and that's really the conclusion from this data. There's a lot of extremely rich dynamics happening on these qubits, and we tested a number of other qubits on this device. Very rich dynamics happening at this sub-second timescale. Okay, pretty interesting. Okay, so now, just like the other teams, we can run even longer measurements. Okay, so now Fabrizio took the weekend off. He started his measurement. Came back. I guess it was a long weekend. That's a 3-day measurement. So he came back and stopped after roughly 70 hours. In this data set, it's a total of 38 million T1 acquisitions. And so just to visualize this, we've downsampled by a factor of 30,000. Otherwise, same thing, a moving average here, and you can bin it in a histogram, and you can assign an average if you so like. Okay, so this is a little bit for the experts in the room, so sorry if I'm losing a few of you here with the technical details. You can, of course, calculate power spectral density of this T1. And so what we did is we took these 2-hour increments and converted that into a power spectral density shown along here, and we can perform fits to that, and we can now kind of have a running average of the power spectral density as a function of time. Okay, fine. The power spectral density, I guess it's been demonstrated in a couple of papers now, is not really a good statistical measure for what's going on here. Something called the Allen deviation is more interesting. Okay, I'm not going to derive for you what the Allen deviation is, I just want to tell you that if there's any non-monotonic feature in the Allen deviation, it means that you have some switching process happening at that time scale on your device. What we find, and to the best of our knowledge this is not seen before, is that there is indeed very rich dynamics happening at our devices at much faster timescales than ever reported before. So if you took a minute to measure T1, you would be able to observe oscillations here and to the right. That would be the only correlations available to you. But what we see in our data is that there's much richer physics happening at these much shorter timescales. Okay? So this was a surprise to us. Finally, we can, at every single one of these lines, we can fit a model to the noise. Okay? Lorentzian, 1/f, and white make a total noise, fit it to the data. And we see very rich dynamics, to put it bluntly, in how the amplitudes of the various noise sources varies in time. And we also see a very strong correlation between the uncertainty of our T1 and the amount of white noise. That's the gray plot here. You see they track each other very nicely. Okay, so I'll leave this kind of advanced statistics for now, and this was a little bit for the experts. I want to return to this beautiful fundamental plot with the frequentist limit on, and now ask ourselves, how close did we get to this limit? And we got this close. Okay, so now there's numbers on the axes. Okay, and in this case, we're roughly a factor of 2 off from how fast you could ever hope to learn T1, unless you're kind of breaking quantum mechanics, okay, which we obviously do not plan to do, so there's still a little bit of ways to go. And if you're like us at the Squid Lab, we think this is enticing and weird. Why are we not close to this limit? And I guess I'll leave you with a cliffhanger and just say, there is actually a protocol that moves even faster than Bayesian and FPGA. This is work in progress in our lab. It's the subject of a future paper. Let me just say that Sven is here somewhere in the audience. Maybe you can raise your hand. Sven and Malte is also here. So if you just cannot wait to hear what's going on with this final limit, please go find them later today. Okay, so I want to return to this diagram. We have this plot on the left. In fact, the time scale is now subseconds. Okay, minutes is just the wrong time scale. There's dynamics at the subsecond time scale. This means that if we're now calibrating on scales of minutes and hours, okay, that's a 5 orders of magnitude difference in the timescales of what's happening on the device and what we're calibrating for. So if you look at this, you should start to shake your hand a little bit and say, okay, what do we do now? Are we just kind of stuck only calibrating kind of average performance, or can we do something better? Obviously, I wouldn't set it up like that if we couldn't do it. Okay, so good. Let's get into this second part of the talk, which is calibration and control in a sub-second environment. Okay, so I encourage you all to think, in light of this data, what does T1 and what does an optimal coherence-limited gate, what does that really mean in the context of something moving this fast, right? Okay, so it could mean just the average instance. Okay, fine, that's what we're doing so far. Seems to work pretty well. You could also say, actually, you should calibrate for the best instance of the device, okay? Only execute your algorithm or your gate calibration whenever the qubit is really performing well, like platinum access to your cloud quantum computer, right? You can certainly do that. That gives you better gate fidelities. But you could also say, actually, what we really should be doing is when the device is worst performing, that's what we should optimize for, to really get the maximal juice out of our processor. And we know from these many beautiful quantum error correction experiments over the last couple of years that we're really limited by the worst performing aspects of the processor, not necessarily the best. Okay? So you could say, actually, just do the best you can in the worst instance. But to even answer that question, you're going to need to calibrate in something like, in this case, 100 milliseconds. 100 milliseconds is the typical timescale of the oscillations or fluctuations that we're seeing in our data. So that's the challenge. Okay? You have to learn every single qubit parameter in about 100 milliseconds if you want to optimize at every point in this curve. Okay, so that's the challenge. Can we do it? Fine. So here's a typical single qubit calibration sequence, just at a high level for now. You're going to do some readout calibration. You're going to work on your single qubit parameters, do something typically called last mile, which means just throw an optimizer at the problem. And then finally, you want to benchmark and see how well did you do. That's the challenge. Okay, so typically readout, you vary a couple of parameters, 2, sometimes 3 parameters. And the typical challenge is something like this. Sweep your readout frequency, sweep your amplitude, find a place in parameter space where your readout infidelity is as small as possible. A fairly standard thing that I'm sure many people in this audience have done. Okay, for single qubit parameters, we're typically executing circuits that somehow amplify an error so that we can find it and correct for it. You end up with these chevron-looking patterns. In this particular case, we're running a long sequence of pi pulses back to back to back to back. And what we're looking for is essentially the symmetry axis right there. Okay, that will be the optimal amplitude of a pi pulse in this specific case. Okay, you're going to be running this last mile business, which means throw an optimizer at the problem. Typically, we sit at some point in a Clifford randomized benchmarking circuit at some depth and just kind of tweak various control parameters until we get, quote unquote, a higher fidelity. Okay? And then finally, you're going to want to benchmark, right? So execute a CRB sequence, fit it, and impress your friends or whoever with your high gate fidelities. Okay? That's the challenge. So now the problem is, okay, if you just want to do this, maybe over Wi-Fi, you've lost almost half your time to just handshaking on the network. Not sending data, just acknowledging the fact that there's an OPX or a Q block or whatever on your network. Okay, so clearly incompatible with 100 milliseconds. Okay, so this will never work. All right, so what can we do? So, okay, again, we return to the well. We have a quantum machine's OPX 1000. It has a very fast FPGA inside of it. And we've built up now a very large toolbox of math executed on the FPGA. So for example, we have a 3-point sampler. This is a technique that lets us find offsets in phases and amplitudes. It takes a microsecond to execute. We have a Nelda-Mead protocol running also on the FPGA. It takes 10 microseconds per call to the iterator. We have an SVM and some Gauss fitting routines, take less than a microsecond. And we have another minimizer that's very fast in 1D, called a golden section minimizer, less than 1 microsecond per call. Okay, now we can put all this together. So here are kind of the details of our calibration protocol. And so your protocol may look a little bit different. I want to emphasize that all the work I'll show you here has been led by Malte Masiniak, a PhD student in our lab, who's also somewhere here today. So here I show in green the standard readout protocol that you're going to be running. And in red, I show what happens on the FPGA. So what we did here is, in the red down here, we ran a Nelda-Mead optimizer, a specific optimizer that takes 3 points and kind of runs a simplex around to minimize with, running for 25 iterations. And you see that it's able to find a point where the readout infidelity is basically 4-ish%, the same as the CPU found. Now, what's nice here is that this took 11 milliseconds. Okay? That's readout in 11 milliseconds. So now, single qubit gates, there's a bunch of measurements here, but I'll just show typical one. Again, in blue is the CPU, like the standard calibration sequence you'd be running. Now, our 3-point estimator, which is an improvement on the 2-point estimator, is able to find this symmetry point in about 2 milliseconds. The last mile, that's a numerical optimizer. In this case, we did a bunch of clever footwork to map together the frequency of drag and the amplitude scaling of drag, and then make a hyperparameter, symmetrize that, and then along that axis, we're running our golden section optimizer. That happens in about 50 milliseconds. And I want to emphasize that what you're seeing here is really sampling at a couple of hundred Clifford gates depth in a randomized benchmarking circuit, every single shot randomized, and then executing the optimizer. And then finally, okay, let's just run CRB, just as always to impress our friends, normal CPU, cross CRB, and here using some optimal sampling theory, and a fitter that's running on the FPGA to get out a gate fidelity. This took about 100 milliseconds. So all in all, here's the time budget for bringing up a single qubit gate on our processor. Okay, 10 milliseconds for readout, 60 milliseconds for parameters, and then roughly 150 milliseconds to get the verification right. Okay, so let me also pause here and say this is part of a large software platform that we've been developing called Pelagic. And let me emphasize here Jacob Hastrup, who's unfortunately not in the audience, but who's really, together with Malte, been the 2 lead architects of this very, very extensible, very, very, very fast framework that's now running each of these protocols as kind of a plug-and-play option when we're calibrating really fast. Here's a snapshot of the data, or the software. I'm not going to go into this, just to say it's 50,000 lines of code. It handles data, it handles differences in measurements. It can step in and out of context, state tomography, and all this stuff. And the idea is to build a framework that's extremely extensible in abstraction, but also lets us interact at a very low level with the hardware. Good. So this brings me to my conclusion. I started by showing you that actually there are dynamics at a sub-second time scale. But luckily, we can also calibrate at that scale. Okay? So just to put a fine point on it, I now put here in blue a box that has the same width as it took to execute all of this single qubit gate calibration. Okay, good. So with that, thank you for your attention. As always, feel free to reach out. we're always looking for excellent students and researchers. And on that topic, allow me one final slide. Let me say that I have been up here talking to you about the results in our lab, but there would be absolutely nothing to talk about had it not been for excellent students and researchers in our lab. So with gratitude to everyone actually working to make stuff like this work in practice, thank you very much. And let me also say that we have a number of posters here at SQA, and you can see them all here, and I invite you to go meet the students and the researchers in the lab. And we have a talk later today by Jen-Hai Soon about intrinsic loss mechanisms in gate mons. And so with that, thank you for your attention.
Thanks a lot, Morten, for this very wonderful talk, walking us through Bayesian updates without being afraid of it now. So now
well, I was also afraid in the beginning.
No, it was very wonderful and super to see what nice results you got. And I think you very well deserve the presents that are already here. But before that, you have to answer all of the questions that are coming right now. So where is the first one? I think it was over there.
Hi, thank you very much. The single qubit gate fidelities that you showed are impressive given the timescales taken to run the calibrations. I'm just wondering how exactly would it scale to do 2 qubit gates within the same time window, and then how do you envision scaling that to like whole processor calibration?
Perfect. Yeah, great. So in this specific instance, we spent as much time validating our gate calibration as we did actually performing the calibration, right? So first of all, in the real context, I don't know if you would validate. You would probably just run, and then if nothing failed, nothing fell out of some threshold that we're running on the FPGA, you just keep going. So if we sit down and we kind of back of the envelope estimate how many protocols are needed to be executed for a 2-qubit calibration, it's of the same order of magnitude, or actually more or less the same number, the parameters that you have to tweak for a 2-qubit gate. So we expect something like a factor of 2, basically, to do a 2-qubit gate. Now, about parallelization, this takes 1 core on the OPX 1000. So you can just count cores, 1 core per qubit. That's at least what it's looking like right now. This really, as far as I understand, cannot be parallelized on the FPGA because we're really using it all the time. Like there's no kind of space to do anything where it's not constantly either measuring or analyzing. At least that's what it looks like now. I have been impressed with FPGA engineers before, so maybe I can be corrected. Yeah.
There was another, please. Yeah.
Is this working? Okay. To what extent are these fluctuations you're measuring due to continuously changing TLS landscape? And have you thought about, instead of just recalibrating, perhaps controlling your TLS landscape with kind of local voltages?
Yep. So we have thought about that, and there's these ideas about cooling down with a voltage bias, and there's even ideas about cooling down with a magnetic field on and turning it off, and so on. We basically just have not explored it. Full stop. We can measure this fast. We see these oscillations. We've, of course, checked it in a couple of qubits, and they're there, but we haven't actually done good A/B testing of how to bring this noise down. Of course, that's subject of further investigation.
Oops, here was a, okay. Sorry, I got overruled.
Maybe pretty quick question, but I feel like a lot of these measurements are a bit agnostic of the previous measurements. How fast would things speed up if you sort of assume a starting point, or even don't necessarily need to be as accurate as the previous measurements because you know the starting points?
Okay, good catch. So here we are using previous information. This is not a cold start, as it's sometimes called. It's not a cold start protocol. The idea is that it'll take time to bring up your processor. The first time you cool it down, frequencies aren't where they should be, coupling strings aren't where they should be. That requires hard work and physics intuition about what's going on. So the way we envision this protocol, and indeed the way we're deploying it in the lab, is you have done your initial calibration. Okay? The idea is you do that once-ish, so it doesn't really matter if it takes 30 minutes or 3 hours, because whatever, it took a month to fab the device. Right? So a couple of extra hours of measurement, that's not really, somewhat doesn't really change anything. So the way that we are running this is that it's basically a toggle in our system. Let's say, before executing your next sequence, whatever you wanted to do the calibration. And the idea is that it's so fast that the user doesn't feel it, right? It's just like executing something in Python, right? You talk about responsiveness and software engineering, and this is kind of built with this idea of responsiveness, which is a sub-second timescale, to be kind of not annoying for the user and have to open up Facebook or whatever while they're working, because they have to wait.
Okay, there was one question here, so but maybe either you throw the ball or I just give it a microphone.
Thank you for this great talk. So you emphasize multiple times the handshake problem, so how much time it takes there. So my question is, are you done in the sense that if you could cut the middleman and have immediate communication, would it actually help you not going to the FPGA but using a powerful computer?
Yes, that depends on the details of the handshake. Okay, so first thing, you will stick in a network cable. Okay, that helps. That brings it from a couple of milliseconds to 1 millisecond, right? So that's a good start already. I guess there are products out there that very intimately put a very powerful CPU very close to the FPGA. I don't know the technical details of the handshake. Maybe you even do, in fact. Yeah. Okay, let me give a more technical answer. Yes, it would help in the sense that you get the flexibility of a CPU, and that's good. Now, on the other hand, the suite of tools that we've developed to run on the FPGA more or less can do everything that you would normally do on a CPU in the context of calibrating qubits, right? So it minimizes, optimally sampling, like the fitting, these things you would normally do. So there is not a lot left, I would say, that you can do in a CPU that you cannot do in an FPGA using our package, with the caveat that, of course, memory constraints is a serious thing, right? So we are thinking pretty hard about memory allocation. So, yeah. So yes and no, I guess.
So Johannes, one short question and a very short answer. Otherwise, you don't get a present.
Thank you. I was wondering what actually happens on FPGA, because it can be very confusing at times. You can put like soft cores of like processors on FPGAs and then run sequential programs there. So when it is actually like 10 times lower than a CPU or ARM core would be, and some chips also have like ARM cores. So are you running actual gateware made out of like lookup tables or AND gates, or is it some soft core and you're running like a sequential program actually?
Yes. So this is QA. So this is the quantum machines. I see a couple of people in T-shirts. This is the quantum machines Python interface to an FPGA. So what's happening under the hood? I think it's maybe proprietary from our friends at Quantum Machines. But what I can tell you is that the timescales that I showed you, they are the benchmarked timescales, not what it says on the box. These are actually the timescales measured in the lab.
Yeah, thank you.
Yeah.
It's like a sequential process then. Thanks.
Yeah. Okay, with this, let's thank Morten again. Yes, you get it.
Perfect.
Thanks. And let's move on to the next talk, which will be given by Arthur Strauss from National University of Singapore. Here we are. And the talk will be about reinforcement learning for real-time context-aware gate calibration with DGX Quantum. So looking forward to the presentation. Stage is yours. Please go ahead.
Is this on? Yes. Okay. Thank you very much for the introduction. It's a great pleasure to be here today and get a chance to present this work. My name is Arthur Strauss. I'm a PhD student at the National University of Singapore, and today I would like to do a very nice based on the amazing background that was introduced by Morten a few minutes ago, it would be very easy to tell you about this story, because it's a continuation of this endeavor of leveraging the core technology that enables the control of our qubits to a level that we hope we can get to make error correction even easier. So, the progress on quantum gates today are really outstanding. We finally reach a stage where error correction is tractable, and the primary condition for making this possible is essentially the idea that you can lower your physical error rates to a certain threshold, right? So once we get to that stage, we can wonder what can we do next, because obviously there are lots of challenges, and when we scale up, the physical error rates might not be also stable, in the sense that we might face emerging phenomenon, some kind of noise sources that you would not have expected if you didn't scale up. And so the main question is, how can we build better controls in such a way that those physical error rates remain stable with scalable systems? So, and an additional comment is that with every improvement you can do in the physical error rate, you can definitely, with the same qubits, do better codes. You can do better resource overhead management. And so we want to wonder, can we really get to the strategy with our control systems today to push the physical error rates even further? All right. So the kind of noise that we try to tackle is really the one that emerges when you are trying to do real thing on the quantum processors at scale. So when you have an idea of executing an algorithm, typically, we wanted to investigate a use case that, if you go only at the single qubit or the two qubit level, this is not necessarily something that you would imagine facing. So classical crosstalk is a very good example of this. So if you imagine you have this variational kind of ansatz on the left side, and you have parametric angles that define your single qubit gates. In the hardware in superconducting qubits, usually what it would amount to is that you play a drive on each individual qubit, which is proportional to the angle that you want to run, right? And so if you do Rabi driving, which is what you would like to do usually when you want to parallelize as much as possible, you will try to play this in parallel, and what happens is that if you have crosstalk, all of a sudden, those angles will trigger a response, a coherent error in this case, on the neighbor qubit. And what's interesting about this noise model, although simplified, is that it already indicates that the circuit structure, so the set of angles we chose in this case, are defining the coherent error in a kind of unique manner. And so you can imagine that if I have classical crosstalk over many, many qubits, I will have this kind of crosstalk matrix represented by those gamma coefficients that you see here that will be directly dependent of the phi representation that we have set in our circuit. So the main question that we wanted to ask is, okay, there are many techniques that we can do to suppress coherent errors. So some will tell you do randomized compiling, some others will tell you perhaps you can try to make your way through dynamical decoupling. But usually the main issue is that you have to add additional gates, perhaps even errors when you try to do this, or you add an overhead in compilation. Because if you do randomized compiling, you have to compile multiple versions of the same circuit, and this definitely takes time and resources on your control system. So instead, what we want to think about is, can we try to suppress, in real time, the coherent error contribution? And for that, we want to leverage the idea that, especially in superconducting qubits, when we have a fixed connectivity, you have building blocks that more or less will remain the same, and we want to open a degree of freedom on those 2-qubit gates that will remain stable. So now we switch from an original CNOT gate that had its own calibration based on what we collected at the characterization stage, and we want to fine-tune its parameterization, represented by this A vector that you see here. And so what it means at the pulse level is that although we still want to execute the CNOT gate, so the unitary we aim to achieve in the circuit is exactly matching the CNOT, its pulse level representation will try to capture a canceling effect of the crosstalk issued by the previous layer, the one which is Bayesian's dynamic, in a sense. So here I'm really suggesting kind of a change of view of what we see as a quantum gate usually, right? Because we want to separate the abstraction between what the logical gate is supposed to do and its physical implementation. And its physical implementation can now be susceptible to modification based on the quantum circuit in which it's surrounded with. And so this entails kind of two main challenges. The first one is the building strategy, and I will show you how we use reinforcement learning and why we used it in a second. And there are the two constraints that we want to comply for this method. The first one is, by construction, the noise awareness. We should make sure that those A1, A2 parameters that we derive and so on are really reflecting the coherent error that is accumulated by the execution of the circuit. And at the same time, we want to avoid a model bias, because if you try to scale up, benchmarking this full crosstalk matrix will become very expensive, and we want to find a shortcut that will enable us only from measurement outcomes to find the right calibration stage. So instead of full characterization, then calibration, we propose a mapping that directly finds the right parameters you should get away for your specific application. But this is not the end of the story, because once you have found those A1, A2 parameters, you also have to wonder how you're going to store them in the memory of the control system. And that's not an easy problem, because if you think about very large fault-tolerant circuits at scale, if you start thinking about each individual instance consisting of a waveform that is different, your control system will suddenly start to face very heavy constraints. So we want to find a way to overcome this constraint over here. And then, as alluded by Morten earlier, there is also the compilation overhead, which comes with the fact that you have to do training, which is why we saw in the previous talk that if you can embed things, the optimizer, into the FPGA, and you can rely on optimizing things on the fly, you avoid yourself the burden that was faced in the paper from Vlad Sivak at Yale in 2023 of applying reinforcement learning when you have lots of back and forth communications between the classical PC and the control system. And the dominant resource time is not so much the quantum execution, which in superconducting qubits will be of the order of microseconds, but really the compilation time and how many waveforms you have to upload in your control system. So again, the main idea is coming up with the technique and making sure that we can apply it without additional overhead, both in the training and in its execution. All right. So reinforcement learning, in a very brief manner, we are talking about something which sits between supervised and unsupervised learning, and it's an interaction between two entities. The agent, represented by this classical neural network on the left, in charge of addressing some actions. Actions mean, in our quantum context, circuit or pulse parameters you'd like to apply on your quantum system. The quantum system in the RL jargon is called the environment, and the objective is that the agent should learn how to find a probability distribution, this pi theta that you see on the screen, which is a probability distribution which will yield with high probability the right actions that enable us to prepare a target state or to calibrate a target gate that we have in mind. But now the key adding that we wanted to emphasize to face this context challenge is to give the network a representation of the circuit. So typically, if I looked at things at the local level in this circuit, I want to switch again to a local version. So I will transform this C0 into a parametric version now, from which I want to find dedicated pulse parameters that will be directly dependent on the circuits in which it's meant to be executed in. So in this case, we decided to give a representation of the angles of rotations that are present in the previous layer. And based on the noise model I briefly mentioned earlier, each phi component will yield its own set of coherent errors on the local qubits. And so the goal of the agent will be to find correlations, the mapping between an input phi and the actions that would yield a high fidelity. And so that's exactly what we did, and we trained the agent. And so the first cool realization is that indeed the agent is able to learn very fast those correlations. So what you see in machine learning is very popular is what we call the learning curve. So in reinforcement learning, we talk about the reward signal directly inferred from measurement outcomes. And we wanted to mimic the execution that we would have on real hardware. So we only gather like the statistics of measurement outcomes we would have collected by measuring different expectation values, for instance, on the hardware. And now the main thing is that we anticipate that the main budget, and so the main training time, is really going to be dominated by the shots time. So we got about 30 million shots to get this full curve converging. And the main question is, how can we make this learning efficient? So to just confirm, we wanted to, once we have the training, of course, we also want to validate our intuition. And so this violin plot that you see is comparing the performance of what we call the baseline, which means if we stuck to the original C0 parameters that didn't take into account this crosstalk context, what is the fidelity on the local subsystem that we would have measured if we didn't do anything else? So here we have a direct mapping, which is going to be dependent of the phi value that we sampled. In our noise model, the bigger the phi value in terms of Euclidean norm, the bigger the noise, and therefore the lower the infidelity. On the other hand, the orange plot shows you that the agent consistently manages to find some actions that compensate each crosstalk signature by each random phi that we sampled. All right, and so now in the last few minutes, I would just want to tell you about how we pursued something very similar to what Morten introduced, which is leveraging the core control technology and the FPGA-based processor to make this learning tractable and fast in the lab. So the starting point of this whole thing is, again, we have this neural network that we don't necessarily want to put on the FPGA just yet, and I'm happy to answer in questions if you, because we are also exploring ways to integrate this in the FPGA, but there's a core question of motivation over here. But now the key insight is as follows. In reinforcement learning, we don't need to send directly the parameters. The agent is not trying to optimize over the actions directly. What it tries to do instead is to evaluate the quality of the policy, namely the probability distribution, represented here as a Gaussian, that generates those actions. And so what we do is at each epoch of training, we are sending the policy parameters themselves. And then everything else happens on the FPGA, meaning that we are going to sample all those actions in real time using a Mueller-Box transform, and going to generate on the fly the pulse parameters that will directly impact the transformation of our circuit. And again, the circuit context as well can be mapped through this parameterization to real-time adjustable pulse parameters. So the communication latency is actually killed because most of the updates are done now in real time. And you can imagine that all the variants of the circuit I would have needed to do to benchmark my quantum circuit are actually done with control flow and parametric adjustments on the FPGA. The rest of the workflow is pretty similar. We send back the reward for further processing. We update the weights and biases of the network, and we do so iteratively until we converge. So we have started to do experimental demonstrations on that, and I encourage you to come see us at Quantum Machines booth, where I will be giving a demo of this working live at the Israeli Quantum Computing Center. And here we just wanted to showcase that the dynamic application of this reinforcement learning was useful, and now we are actively investigating how we can map this crosstalk matrix and learn correlations between different angles. And the circuit, the Qiskit circuit that you see over here, is the exact mapping of what is going on in hardware. So instead of compiling different versions of the same circuit, which is usually what you need to do when you want to compute multiple observables or when you do tomographic protocols, here we do that all on the, it is pre-compiled all on the FPGA with this control flow structure. Conclusion, I hope I convinced you that the control system technology that we have today really opens doors for scalability at no additional overhead if we play things right. So we need to come up with better abstraction layers that enable us to really leverage the maximum of this technology and play it with additional algorithms inside. And for now, what we are currently investigating is how to embed even more this strategy of context-aware calibration within error correction workflows. And the idea now would be, similarly to this Google paper that came out a few years ago, to use syndrome data that naturally comes out of error correction to influence the way we are changing the gate parameters at the pulse level. And this is a really exciting direction, and I'm happy to take it offline and answer questions if you have any on this. I would like to acknowledge my colleagues from the National University of Singapore, and especially Aniket from Oxford University, who made all the simulations run in a super fast time. So with that, I would thank you very much for your attention.
Thanks. Thanks, Arno, for telling us how to use reinforcement learning for using better calibration and for understanding better our devices. So please, the board is open for discussions and questions. Here's one. Johannes, can you just throw the cube to the second row?
Thank you. Very interesting talk. My question goes, or I would like to have your view regarding other mechanisms as machine learning. So, for example, supervised learning, unsupervised learning, or maybe large language models. Do you see that space for within your scope for integrating?
That's a great question, indeed. So for now, what we did as an early demonstration was a neural network which is fully connected. So a really simple layer, because the input encoding of the circuits, so if I go back to this representation, was really easy to embed. So we have a variational layer which contains a few angles that you can give a straightforward input neuron to this observable. Now, we are thinking about extending this to more complex circuits. So one which carry structure that, for example, would involve different connectivity between the CNOTs, and we really want to think about this network to learn correlations between arbitrary quantum circuits and the right set of actions. And so the plan for us is to really investigate how we could do graph neural networks, for example, to encode circuits encodings, and that will enable us to indeed train. And the main question is, how do we do it at scale? Because for now I talked only about one gate at a time, and what we're investigating next is how we can do a multi-agent kind of thing. So you will have a big network representation that will try to act on the same circuit with different parameters, and we collect a bunch of rewards all over the place.
Thank you.
Is there a further question? There is one further question, Chris. Yep.
Thank you for the nice talk. How robust is the reinforcement learning strategies you're adopting in the presence of noise? Do you need to adapt it to include maybe more physics-motivated nodes in your graph or anything to get the most power out of it?
So on the reinforcement learning part, what is the reason why it was adopted in a few previous works and why we chose it as well is the fact that it does not rely necessarily on the description of a model. So by construction, it's supposedly model-free. Now, of course, you can ask the question about what kind of noise model can I hope to counteract, right? And usually the answer will largely depend on the action parameters that you decide to play in. So in this case, and for the purpose of not adding any overhead on the compilation, we do only some kind of optimal control or adjustments of the gate parameters, right? So in this manner, you can only hope to correct coherent noise, in a sense. If you wanted to do something a bit more longer term, like drift handling, for example, we would have to see if the action space could include dynamical decoupling sequences, some things like that. It could definitely be incorporated, and we're actually working on an architecture at the software level that can enable us to break the things down. But for now, we are kind of limited by construction of the action space of the coherent noise.
So thanks again for the wonderful talk and for the questions are answered. So thanks.
Thank you very much.
For Arthur, and also a present for you. Thank you. Thanks a lot. And with that, we are moving on to our next speaker. It's Alexandra Ramoa from the Iberian Nanotechnology Lab, who will tell us about the characterization of superconducting qubits in a low data regime. Here, please. Sorry, Alexandra, here. I think you get a microphone. Yeah. Any urgent announcements? Okay. Now we're almost there. I haven't prepared any jokes on superconducting qubits. I don't know if someone has one. No, so now we're back. So welcome again, Alexandra, and we're looking forward to your presentation. Please.
Thank you. So good morning. I'm having some ear and jaw issues, so apologies in advance if my communication is subpar, but I will try my best. So I'll be talking about the characterization of superconducting qubits in a low data regime. In particular, I did some experiments on IBM hardware to perform parameter estimation. And I did these experiments using Bayesian inference for parameter learning. Just for a short overview of Bayesian inference for quantum characterization, I have this very simple example where I have a time-independent Hamiltonian that induces oscillations in the Box sphere, or rather in the measurement probabilities. You can think of a block vector processing around the x-axis, for instance. And this causes the probability of measuring 1 in the z basis to oscillate as the sine squared of a frequency, omega, times the time t. So here the problem is we want to estimate the unknown frequency, omega, and what we can do is making measurements for a controllable evolution time, t. And in the traditional approach, the frequentist approach, we will do this by making measurements for a specific time, t, and then inverting the relative frequency to calculate it directly. So here, for instance, for time t equals 0, we have that omega would be the arc of the sine of the square root of the relative frequency. If we wanted to make measurements for different times, then we would do something like Kerr fitting. In the Bayesian approach, instead, we have a probability distribution that we can evaluate for any possible value of the parameter. That is, our result is given not by a single point estimate, but by a probability distribution that quantifies the merit of any possible value that omega can take. And we extract results from this probability distribution by integrating over it. We can integrate an estimator, getting an estimate of the frequency. We can also integrate, for instance, the standard deviation to get an estimate of the uncertainty. And in this case, we don't need to generalize anything if we want to use different times. This is a more general approach that can deal with a fixed time as well as it can deal with various measurement times. So apart from, for instance, immediately offering estimates of the uncertainty, the main advantages of Bayesian inference are, one, the robustness of integration, which is quite more solid than optimization, especially for multi-parameter estimation. And second, that we can optimize the experimental design. And this is because in addition to expectation values of things like the estimator or the uncertainty, we can also calculate the expected value of utility functions. For instance, we can calculate the uncertainty in a look-ahead scheme and choose the times, in the previous example, this time t. We can choose the times which are, in this case, an experimental control to minimize the uncertainty that we get. As for the challenges that we get with Bayesian inference, they're tightly related to the advantages, as you can see. So the robustness of integration is only applicable if we have robust integration methods, which is complicated, especially for multidimensional spaces, as arise for complex quantum models. And the second one is that the ability to optimize experimental design is only useful if we use it right. So we have to find ways that are cost-efficient to optimize experimental design. So in this work, I tackle these 2 points. On the robust integration front, by applying advanced statistical techniques, namely Markov chain Monte Carlo, Hamiltonian Monte Carlo, which can or cannot be a form of Markov chain Monte Carlo, temporal likelihood estimation, subsampling strategies, and so on. As for the experimental design, I essentially applied some approaches that are problem-tailored, heuristics to define the search range adaptively, and so forth, to reduce the experimental optimization cost while maintaining the good results. So skipping to some results, here is the result of a Han-Echo experiment for a single qubit from the IBM hardware. These gray points represent data points that I collected from the device using pulse measurements, and the dashed black curve is the curve produced by the Qiskit filter, the default filter from IBM, which was based on the gray points. And the red curve is my approach using Bayesian inference, and it used not these gray data points, but only around 4% of the data contained in these data points. And as you can see, the results are quite similar. And looking at the standard deviation that was produced, this still holds. The standard deviation was quite similar for the Bayesian inference method I applied versus the Qiskit filter, despite the Bayesian inference, using 15 times less measurements. And conversely, if we try to match the Qiskit filter to this low data regime, we get an uncertainty that is much higher. So actually, if we use the exact same data that we use for Bayesian inference for the Qiskit filter, we get infinite uncertainty. If we try to rearrange the number of shots across better times, optimizing this distribution, then we get this uncertainty of 14, which is roughly 3 times larger than that of Bayesian inference, using the exact same number of quantum data. So clearly, Bayesian inference excels in low data regimes, where the number of measurements that we can perform on the quantum system is limited. Going forth to a Ramsey experiment, here I consider 2 parameters, the tuning frequency and the coherence time, and we estimate them both at the same time. There are some trade-offs here, for instance, for the experimental design, because what is optimal for one parameter is not optimal for the other, and this also translates into differences in the learning rates. Here we can see that the frequency has a faster learning curve, and the coherence time takes longer to learn, and this is due to the dependence of the generative model, which is the likelihood on each of the parameters. But even still, and even with noise, in a quantum device, Casablanca, we saw that the estimation of the frequency alone was still quantum enhanced, falling somewhere between the standard quantum limit and the Heisenberg limit. And this is in spite of the fact that we had to estimate both quantities at the same time, so the frequency and the coherence time, assuming that neither of them was known in advance. So comparing again to the Qiskit default filters, here we have the same curve as before, and in this case, the curves are even more indistinguishable. So here are, again, the dashed black line is the Qiskit filter results, and the red line is the result of the Bayesian inference algorithm I applied, and they're nearly indistinguishable. And Bayesian inference used even less data with a 99.6 reduction as compared to the curve fitting that Qiskit used. This is also interesting because the time fluctuations of these quantities can be quite strong. And for instance, for calibration, we don't want to have a method that takes very long to estimate the quantities so that we can calibrate our gates and find the resonance frequency. And here is the time evolution of the resonance frequency and the coherence time of an IBM superconducting qubit as a function of time. And we can see that the fluctuations are quite strong. This wouldn't have been captured if we had a method that takes long to estimate these quantities, because we cannot pinpoint what the frequency or what the coherence time is with a quick estimation. So lastly, another experiment I performed was an echoed Ramsey experiment where I introduced an extra pulse to increase the coherence time. So this basically makes the oscillations be less damp. And to further enhance the data saving abilities or the quantum measurement saving abilities of Bayesian inference, I used a subsampling strategy. More specifically, blocks to the marginal metropolis with around 40% of the observations subsampled. And these are the final probability distributions which convey our results, comparing full data Bayesian inference to subsampled Bayesian inference at 40%. And as you can see, the graphs are pretty similar. The black curve is the original distribution based on the full quantum data set. And the red curve is the subsample distribution, which is actually slightly sharper, so there's a slightly smaller standard deviation, even though it's not very significant. This is also due to the use of control variates, which are very good in this case and can help out quite much. So one of the other issue that I mentioned of experimental design has had some proposed heuristics to cut down the processing costs and not do full-blown experimental design, but instead use lower-cost strategies that can still perform quite well. However, these strategies are not very generalizable, and in particular, they often make assumptions about the probability distribution, such as unimodality. And probability distributions, in the case of quantum characterization, can be multimodal, be it to intrinsic issues like the model definition, or due to extrinsic problems like in multidimensional spaces, the data tends not to be enough to be unambiguous from the outset. So I developed a lower cost strategy for experimental design that still preserves the qualities of full-blown experimental design without going, while saving the costs, without going so far as to be less general. And these are the results of this strategy, which basically defines the search range adaptively as the inference proceeds. In the left side, I have the noiseless or ideal case without incoherence, and we can see that the Heisenberg limit is achieved. In the case on the right, it's the noisy case with a limited coherence, pretty small coherence. There's a slight quantum enhancement, which we can see with numerics, even though it's more limited. And this is compared to the state-of-the-art of other frequency estimation heuristics. And you can see both in the noiseless and the noisy case that the strategies that I developed, which are in blue and in green, perform best. They have more stable behavior in the noiseless case, and in the noisy case, they do better because they still can consider the full model, including noise, whereas the other ones cannot. Another application of this type of strategy, because it's very general, is phase estimation or amplitude estimation. So here is an example with amplitude estimation, where we want to find the measurement probability or estimate the measurement probability associated with a given subspace for a wave function. And in the left is the noiseless case again. The strategy saturates the Heisenberg limit again. And in the noisy case, it still achieves quantum enhanced estimation, although falling short of Heisenberg limited scaling. And again, compared to the state-of-the-art of quantum amplitude estimation algorithms, we have that both in the noiseless and in the noisy case, this Bayesian low-cost experimental design approach performs best. These are the relevant, some relevant preprints whose results I presented in this talk, in case anyone is interested.
Thanks a lot. Thanks, Alejandra, for telling us that we all probably take too much data and we should basically a bit more cautious and save time on data taking. There is questions. Board is open for questions and discussions. There is one, please. Where is the cube? Chris.
Hi, thanks for the great talk. Can I just ask like a clarifying question first, which is that with those experimental designs, basically what you're doing is, are you like collecting all the data and then the Bayesian model tells you like where to look for the next point based on the points that you have, or do you have like, how do you select the data exactly? If you said 4%, 0.4%, so how do you select which points do you use?
So in the Bayesian inference case, we choose each experimental control, which is the evolution time per iteration. So we choose a measurement time, and then we choose another measurement time, and so on.
So based on the data that you collect on the first measurement?
Yes, there's adaptivity, which can be adjusted, so we can have a bigger look ahead, so that we have parallelization abilities. But in general, it's adaptive, yes. And in the case of the Qiskit fit, I just optimized the measurement times.
Okay, and if you have you tried like doing it fully non-adaptively, like just setting some kind of? Is it possible to set some times like some ahead of time, and this still be better, or is the whole strength coming from this adaptiveness?
Oh no, it's still much better. Yes. So there are similar reductions if we do offline measurements, because it's kind of intrinsic to Bayesian inference that it deals better. Because, for instance, in this type of graph where we have the oscillations, Bayesian inference doesn't need to resolve the graph. So if we have, for instance, in this case, 5 shots per point, the curve will be very noisy, and the curve fitting will fail. But Bayesian inference can still do that because it's not relying on drawing a curve around the points. So it still has a significant data reduction.
Okay, thank you.
Thank you.
Is there another question? Maybe I would have one. So because you are showing that the data reduction rate is somewhere between, what was it, 0.4% for one experiment and then 4% for the other one. Is there some kind of guidance or some kind of also analytical understanding how much data reduction I will get for some experimental design or for specific experiments?
It really depends on the dependence of the measurement probabilities on each parameter, because the first parameter has an exponential dependence on the likelihood function, and the second one is a frequency, so it's more sensitive to variations. And this, and in particular, the fitter does better with this type of curve, because this is easier to fit. You can, even with low data, it's kind of easy to resolve. Whereas if here I start cutting down the number of shots per point, it's going to be very, very noisy. So curve fitting is particularly bad for this.
Okay, but it's hard to say in advance basically how much data I should take to get the best fitting. But we can discuss.
I mean, qualitatively, it's easy to get an idea. Quantitatively, I think it's difficult without actually performing the experiment.
Okay, thanks. Then thanks again.
Thank you.
For the very nice talk. You also get a present for us. Thanks. And with that, we move on to the last speaker of this session, which is Elena Lupo from Forschungszentrum Jülich, who will tell us about the charge-basis tomographic protocol for superconducting qubits. Please, stage is yours.
Okay. I'm gonna present a work that hopefully will help studying the Hamiltonian of superconducting circuit for application to quantum computing. And the main motivation stands on the fact that when we work with superconducting qubits, we're working with Hamiltonian models that are intrinsically multi-level systems, and they are usually analyzed via spectroscopic techniques. Well, sometimes the essential physics behind this physical platform can evade the Hamiltonian model validation. An example of that is the only recent detection of high harmonics in a tunnel aluminum oxide Josephson junction. And this has been done via the spectroscopy to much higher level, much higher energy levels. And so we can already see what could be the limitation of validating a Hamiltonian via spectroscopy. The first one being the fact that we usually have access to very limited spectra, and to fit the parameters of the model we want to validate. And the coherence in the system usually broaden the lines in the spectrum measurements, and jeopardizing our ability to detect weaker interaction or a subtle effect. And another thing is that using the spectroscopy, correlations that are within the junction or the weak links that we are using can be hidden using these techniques. And so we try to find a method for actually expanding the analysis to, for instance, novel qubit designs, where the potential can be of different types in the Hamiltonian, or some exotic Josephson junction, where you can also hide intrinsic fermionic degrees of freedom or even topological ones. And so if we look at the quantum state tomography technique, this has been applied to a variety of different systems for the state reconstruction of optical photons, electronic states, or in the case of superconducting circuits, superconducting cavity states. And actually we want to focus on superconducting cavity quantum state tomography that has been applied for both the reconstruction of prepared cavity state superposition, so where we know the Hamiltonian of the system, or we assume we know, or for the refinement of only perturbative Hamiltonian models by looking at states that we assume we know all about. And so we want to take inspiration from this for finding a method to potentially explore other type of superconducting circuits. And so we first look at the usual protocol for quantum state tomography in these platforms, and it involves the preparation of different state of the target system we want to analyze, and its evolution, combined evolution with a probe qubit. And the measurement of the probe qubit, then it is done in its energy basis for the reconstruction of the density state still in the energy basis. And there are a few works on it. This is a well-known technique, and we want to and this relies on a few key elements, which is the high coherence of the system. The fact that the coupling between the target circuit and the probe qubit commutes with the uncoupled Hamiltonian, and the fact that the coupling element is actually available in the system. And so we want to go a bit further and see if we want to analyze systems where the high coherence cannot be achieved. Well, we can think of focusing on the ground state of the system, but then we don't want to reconstruct it in a trivial basis like an energy basis, so we cannot use that, and that's why the idea of analyzing it in the charge basis comes from. If we don't have if the commutator between the coupling and the uncoupled Hamiltonian doesn't commute, then we want to find a way to avoid the fast dynamics in the system. And if we also don't have this available yet, okay, we need to engineer it. So for our protocol, we focus on a Hamiltonian that can be represented by 1 degree of freedom in this work, and where the Josephson potential is a function of the ladder operator of the charge state, for instance, across a junction that is in the circuit. This could be, for instance, an SIS junction or an hybrid junction with hidden degrees of freedom. We want to reconstruct the density matrix in the charge basis, and so we need a coupling term that couples the charge basis of this island in the circuit with the longitudinal coupling of the qubit. And we, in parallel with the preparation of the state in different of the target circuit in different states, here we want to prepare the target states in different ground states, and we vary the Josephson energy of our Hamiltonian model. And the eventual aim is not only the reconstruction of the density matrix, but the actual validation of the model Hamiltonian. For the measurement protocol, it's very basic. We want to avoid fast dynamics. We want to shut down the Josephson energy of the potential and turn on the coupling at the time of the measurements. And we know that if we put the probe qubit in a superposition of the ground and the excited state, we can actually see that we can extract the population of the charge states that compose our target Hamiltonian state. And in this system, it's trivial that we need a switch-off element, an element that can switch off the, ideally, completely the Josephson energy. For instance, a split junction. For the reconstruction of the ground state, well, we're not applying fast operations on the target circuit, but we can represent the preparation of each ground state as an adiabatic evolution between the state we want to reconstruct and the states of the system that we measure. And in this way, we can use the least square regression for the reconstruction of the density matrix. In these equations, we don't know neither the form of the density matrix or the model. We also want to validate the model that we assume for constructing these equations. And this can be done actually with using the Hilbert-Smith distance in the following way. So we take as a target circuit, for instance, the transmon Hamiltonian with adapted nonlinearity, and we think about it as the true Hamiltonian, where we simulate the measurements of our density matrix. And then we reconstruct the density matrix using a series of Hamiltonians with different nonlinearities, including also the one of the transmon Hamiltonian. And then we compare the density matrix that we reconstruct with this different method with the one that is expected by using these models that we use for reconstructing. And we actually see that with the looking at the Hilbert-Smith distance between these density matrix, that we have a neat way to distinguish which Hamiltonian we used as, we assumed as the true Hamiltonian of the system. And so this hopefully can be a way to analyze Hamiltonian of different size in those systems where spectroscopy cannot be really useful. Another important part of the protocol is the coupling elements between the target and the circuit. That wants to couple this charge operator with the longitudinal coupling of the probe qubit. And for this, we use as a probe qubit a split flux qubit, and we couple one of the island of the split small junction that control the frequency of the flux qubit with capacitively with the island. In this case, we use also a resonator for tuning the coupling for the protocol. And so in this way, we can actually see that the effective Hamiltonian lead through the Aron-Kasher effect, some longitudinal coupling, and there are some parameters of this system where we have the transverse coupling completely shut off, and we have a known zero value of this longitudinal coupling. And as a further application, I refer also to another work of us, led by Daniel Dan, where we show that in a system where we have a hybrid junction with a quantum dot, that's with also added Majorana fermions, that we see distinctive features in the charge basis representation of the ground state, where fractional charges appears that these are features that represent the fact that there are these additional degrees of freedom in the junctions. So potentially we can use this tomographic protocol for analyzing this system, and we also see that in the entanglement spectrum that can be constructed using this tomographic protocol. And with that, I thank you all. It's a bit late for the posters on Tuesday, but check out the poster of Ashutosh today.
Thanks, Elena, for this very interesting talk about measuring target systems using superconducting circuits. Questions? I don't see any questions. Maybe let me ask, because it wasn't clear for me. So what is the target system? That can be any system. Or is there any constraints on the Hamiltonian that describes the target system?
So at the moment, we are using a normal, it can be any, we use a system where there's only 1 degree of freedom in the charge basis at the moment, but potentially we can also apply this with multiple charge elements if we have more probe qubits. Because when we look at the probe qubits, we only project the Hamiltonian in the charge basis of that degree of freedom, right?
So basically each island has then a charge representation or a charge basis, and then you would have 1 probe qubit for each of these degrees of freedom that you would have.
I think it can be extended to that.
Okay, and the probe qubit, because now it seems to be quite complicated. It's not just the transmon, it's just the...
No, the probe qubit is the flux qubit. Because we want to, for doing this element, we want to have the target qubit to be coupled to the longitudinal degree of freedom, and essentially by coupling it with the island. So usually you have the 3-junction superconducting circuit with the alpha junction, which is the reduced junctions. That parameter changes the splitting of the flux qubit. So by splitting it and using the Aaron-Kasher effect, we actually can couple with it.
Okay, so you need this longitudinal coupling term. There was one question here. The cube is over there. The one person in red shirt, can you just throw it to the second row? Almost. Didn't work anyhow. So.
Thank you very much for your nice presentation. My question goes in extending maybe these superconducting circuit Hamiltonians from superconducting, interacting with modes on the cavities, for example. Have you considered that one? So if I want to transfer the quantum states, for example, from one quantum chip to another quantum chip.
There are some in the cavity state tomography. They do construct these Offines et al. Reference. They do construct Fock states in the cavity, if that's what you mean, using a probe qubit 2-level system. So that's kind of the parallelism. So we have a multi-level system for us and a probe qubit. But we want just to read it, essentially. Yeah, so for the cavities, is this one the reference?
Okay, thanks. Let's thank Jelena again for this wonderful presentation. And also let's thank all of the speakers of the session. And with that, we move on to the coffee break, which will last now until 11:30 or 11:15. Kristen. And I forgot the present. Sorry.
Yeah, thank you.
asking how to begin again. If you're strange and I would love to meet you, I can't go on any other way. Been on my own too long to retreat. You're just getting too old too late.
Okay, welcome back to the next session. Before we get started, just a quick announcement. We had a few questions whether the dinner tonight is really actually in the church, and yes, it's really actually in the church. And actually the real old Dutch kings are buried below the ground, so you will actually sit on top of the old Dutch kings and queens. So that's a real thing. With that, I'll give the floor to Michaela Eichinger, who will present the next session.
Hello, everyone. Yeah, it's an absolute pleasure to host this next session. I'm Michaela Eichinger from Quantum Machines. And yeah, this session will be on coupling and modeling of superconducting qubits. And we will kick it off with an invited talk by Max Werdinghaus from the Walter Meissner Institute. And he will tell us more about the PMON.
Right. Thank you for the nice introduction. Having a nice time so far also at the conference, so great effort there. Right, so I'm talking today about one of our alternative qubits that we are building and we find promising. And in this prototype, I will show you a bit more what we can learn about how this qubit can a bit decouple from its noisy environment and so on. We are doing this with a collaboration with the BMW group, and we're doing this in the context of the larger efforts of our institute, which is the Walter Meissner Institute in Munich. So all the things that I'm telling you are published in these two papers. I'll also have them on the slides throughout the talk. And then I'll give you a bit of an outlook later on also what we are going to do with that next. So for context, in the Walter Meissner Institute, we are doing scalable superconducting quantum computing, and we are doing a full stack approach. So we are doing, of course, this is all based on the development of quantum chips, and we are very much focusing on novel architectures here. And we are, of course, beyond that, actively collaborating and developing all parts of the stack, so from the cryogenic infrastructure over the control devices that in the end give us the microwave signals. Of course, we have a software environment, and we want to also expose this to an application layer because we do want to, of course, do holistic benchmarks to see how our novel elements in qubits in the end affect also quantum error correction and applications. If we zoom in here, because we are talking about the hardware and the architecture, so what you see here is our current working horse, which is just fixed frequency transmons with tunable couplers in the by now well-known error correction baseline architecture. And of course, so we focus here on scalable chip design and operation. We're targeting error-corrected architectures. We are utilizing here the high-quality fabrication that we've built over the years, and our goal is to replace building blocks of the QPU with more advanced components. So if we look a bit closer at the components of the QPU, we can see here, this is currently our qubit structures, and they are, the interactions of them are mediated via tunable couplers, and of course both of those have control lines that let us control the individual elements here. So now we want to replace some of them, and in this talk I'll focus on our qubit unit, which means we want to, in the end, replace this, have a similar large-scale effort based on the novel qubits that I'm going to show you today. So for the outline of the exact talk, because I'm talking a bit about two topics, mainly because it's all in the context of isolation from noise and how to avoid noise affecting your qubits. So in the first very brief overview, I want to quickly give you an insight into a nice experiment that we did where we tried subharmonic driving, in this case of fluxonium qubits. And then for the majority of the talk, I will be talking about our new PMON multimode qubit. And in the outlook, I'm also going over a multi-PMON architecture, how we are doing there and how this could look like going forward. I also want to advertise, so we have posters on both of these, so check out Frederick Pfeiffer's on the PMON and Florian Wallner's on the subharmonic driving. And then, yeah, with that, let's get into it. So what's the motivation? In the end, for superconducting qubits and in quantum computing in general, there's a controllability trade-off. So you want to have a qubit that is largely protected from any influx of noise. And this noise is, of course, coming from the environment, but also you need certain auxiliary elements. So, for instance, there's coupling to readout elements, and there's coupling to the control environment. So what is the idea here for the first experiment I want to quickly show you is that of course there's a noise influx over both of these channels. And in this case, the circuit is actually a fluxonium, which has a DC flux line to control its energy landscape. So we want to use this now to also exert control, which is typically not what you're doing. So typically you have a dedicated microwave line also. And of course, there's a challenge because over the flux line, it's relatively easy to decay into your environment. The solution is that we apply filtering and we go below the qubit frequency with our control. And this is then possible via doing n-photon drives to do still deterministic control of your qubit. For those that are not familiar with the fluxonium, very quick introduction here. So it's basically a circuit that is very heavy and strong inductance built in here. And this gives rise to the emergence of a symmetric potential well structure where then the qubit states are encoded in the first still bottom levels here, but they are separated by this barrier which makes the qubit intrinsically protected against T1 decay. And we can design these in the range of up to 1.5 gigahertz, so they are typically much lower in frequency. Here you can see actually the circuit. So we see here, this is the flux line that we're going to be using to try and control it, but also for transparency, we do have a microwave line because we want to also have a baseline to compare these efforts to. So, okay, what's the setup? So we have a fluxonium here, and we are trying now to couple a flux line inductively. So this is sitting at the 3 Kelvin stage, and from that on, we are not blocking any noise anymore. So typically, that's a very bad idea, and you see this also if you apply this control line unfiltered, which is what you would have to do resonant control. You get relatively bad coherence and lifetimes here, which is so no magic here. This is known. If you don't filter your noise, then your qubit will suffer. And if we now apply what is typically done to the flux line, a low-pass filter that is sitting below the qubit frequency, the KPIs here drastically improve. So the most significant impact is on the T2 echo time, where we get a 10-fold improvement. So far, all known. This is what you typically do to your flux lines, but now we want to also use this as a control mechanism. And there we tried now a subharmonic multi-photon transition drive, and we tested basically at multiple, at certain multiple photon transitions, how well the control is still acting. And our main result here is that we can get relatively close to the performance of the standard microwave drive. So what you see here, this is now for a 3-photon transition. And the red line is what we achieve in the performance of the qubit, compared to an unfiltered performance that is very much worse. But we get very close, actually, the difference is 99.94 compared to 99.96 in fidelity to the resonant microwave drive. So with this, we are hoping that we can reduce actually the wiring that we need for such flux qubits, where we can then hopefully use the flux line directly to also implement control signals and just cut the wiring in half that is required to control these qubits. So this is a very nice experiment that I wanted to quickly show you. If you want to go a bit deeper, there's a paper on it out, and also we are releasing a theory paper on why the multi-photon drive works. Soon, so also if you're interested, check that out or talk to Klaus, who is here in the audience also. Okay, then moving on to the main part of the talk. So why we are thinking about the PMON is the same motivation, really. We want to have a protected circuit. And what we are tackling with is the coupling to control and readout environments or other quantum systems that are necessary, of course, to operate a large-scale quantum chip. So the challenge here is then to prevent decoherence mechanisms through these coupling channels and shield the qubit from it. And the conceptual idea here is that you encode the qubit and you separate the interaction with the environment largely through a mediator mode. Where this mediator mode then has a certain coupling to the qubit that protects you from most of the Purcell decay and dephasing. So, quick recap on how this typically works. Typically, the qubit would be directly coupled via an exchange Hamiltonian to your readout resonator. In order to be protected from actual photons going into the resonator, you would typically put them at a certain distance and frequency. And here you can see how this looks like in a circuit. This is what you immediately get if you capacitively couple these two components. So then, going then a certain distance away in frequency will give you a dispersive interaction, so the photon exchange will not be happening anymore, and your interaction Hamiltonian will transform into this non-direct interaction where you just have a frequency shift depending on the qubit state exerted on the resonator, and that's exactly what we use then for the readout mechanism. The problems with that then is that, of course, so since there is this linear coupling term, this will never go away. Even if you put it far away, there will be a remaining Purcell effect, which you typically suppress by the detuning. Still, it is remaining, and it can limit your T1 times. And then what is also a huge concern is that, of course, so in a perfect world, the resonator is always empty, but due to thermal population, you will have some photons here, and you will have an equivalent back action on the qubit, which will then change the frequency and in the end affect your T2 time of the qubit. So to solve this problem then, there's a couple of proposals. You can actively control the coupling component here. So for instance, we do this between couplers with between qubits with tunable couplers. We can avoid linear couplings altogether, and here we are choosing an approach that combines these two somewhat. So what this then motivates is the setup that I showed you before. So what we want to build here is an interaction Hamiltonian that couples the qubit weakly to a mediator mode and with the indirect coupling in the first place, so you don't have an exchange interaction here. And then this mediator mode is free to have the exchange interaction when talking to the resonator. And what this then gives you in the end, if you also go into the dispersive regime, you have still a mediated dispersive shift of the resonator depending on the qubit state, which then takes a slightly different form. But to first place, you have your qubit not interacting with the resonator and therefore being also largely independent of Purcell decay. And then the advantage is that you have the Purcell protection, and you even can control the dispersive coupling by still tuning your mediator. There's still, of course, a remaining challenge. So we are still having open questions on how the tunability of the mediators should look like exactly. And we, of course, get a slightly larger footprint because it's not just a qubit circuit, but we have now mediator elements also in that. Great. So how does that look like in practice? So we can design now a circuit which consists of a couple of nodes. That looks like this, which encodes both the qubit and the mediator at the same time. So how this works is, in the end, there's a couple of modes living in this circuit. And the qubit mode, for instance, is a fixed frequency mode. There's a tunable squid element here. This mode is not interacting with that. It's living entirely in the static elements of the circuit, and so it would be first order flux independent, which is one criterion that we want for a stable qubit. Then there is a second mode emerging that is the mediator, which lives also in the squid loop and therefore is tunable, which is useful to then tune the interactions as well. And there's a third mode emerging, which we, by design, shift to very high frequencies, so it basically never comes into play when we use this circuit. And then due to the overlap of the two modes that live in the circuit here on the two lower nodes here, we have exactly this cross-Kerr coupling term that we wanted to design to the mediator mode in the first place. So this is now a non-photon exchange interaction, and is virtually what you get if you do a dispersive coupling with the direct coupling mode, but you get it just intrinsically because these modes live in the same circuit. Here's what it looks like in the initial design that we did. So we have the three islands here in these round structures, and they couple then via the Josephson junctions to a central island. Here you can see the Josephson junction setup, and what then emerges is kind of what we have been promising. So you have then a tunable mode, which is the blue mode that I showed you before, which crosses in the end the stable qubit mode here, which is largely flux independent. If you look closely at this design, there's relatively obvious that we didn't get rid of the direct coupling, because then there would be no avoided crossing emerging here. That is not entirely by accident. So you need to meet a symmetry concern if you want to have this completely go away. But in the first iteration of this, we also opted for this coupling because so it will take away controllability and everything. So we want to test a couple of things at a time. And I will show you now in the later half of this talk that we still can show the properties that we envisioned for this qubit. Still, for full disclosure, this has a direct coupling, but we can still test the effects of the circuit. The third, the resonator mode is here above, and this also gives then emergence to a dedicated readout point where we can put the mediator mode at the highest frequency, and this will then strengthen the interaction with the resonator. And there is a control point, which is exactly when you tune the mediator mode far away. So the interaction with the resonator will be largely suppressed, and you will have the qubit in a very, very isolated state. You can see this into first hand from the T2 times that emerge from this circuit. At the readout mode, the qubit, at the readout point, the qubit mode has 84 microseconds of coherence time, and at the control point, we get 150. So double, twice-fold improvement, and we can look a bit further also into that. What's the effects that come into play to diminish the coherence at the readout point? So what happens if you look at the dispersive coupling? So we can theoretically and practically test this. So you see at the readout point over here, you get a very strong dispersive interaction with the resonator. So you have a good position to do qubit readout. And then as you move into the control region, this virtually goes away very much close to zero. And what we can see here now is also what we plotted in these dashed lines and dotted lines here, is the direct interaction, which is coming from this effect that I told you before, this slight direct interaction that we still allow. It is relatively minimal, and it goes largely away at the control point as well, because we detune the mediator mode a lot from the resonator. But then the indirect chi shift actually takes care of the majority of the effect that we are observing here, and allows us then actually to have this very nice on-off ratio of the interaction with our readout circuit. We can also test this immediately further and check what a population in the resonator will now do to your qubit. And this is, for instance, so we are simulating here temperature, really. We are controlling the average photon number in the resonator circuit, which, as you can see at the readout point, it will drastically and quickly diminish the coherence times of your qubit. Of course, this is a relatively extreme photon number, and you would not have that by temperature, but it's a very nice demonstration of the effect that we are trying to show here. And then at the control point, you see we can pump the resonator full of photons virtually, and it will not at all notice that, exactly because of this point that you virtually have no frequency interaction with the resonator anymore. There's more effects that we can look at. So if we now really look at the T2 and the T2 echo times around these 2 points, we can see a couple of the effects in action. There's actually a lot that you can observe here. So of course, there's the influx of flux noise. Even the indirect coupling will relay the flux noise that the mediator mode experiences onto your qubit mode. And that means if you are into a high derivative region of the flux, you will, of course, have diminished T2 times. And this is seen as well as you tune away from these sweet spots where the first derivative is 0. You get a diminishing return in the T2 times. Interestingly, as you tune away, the interaction with the resonator actually lets your T2 time go up while your T2 start time goes down. So that is a nice demonstration of the filtering effects that both of these things do. So where the one really starts to suffer from the flux noise that you're now experiencing, and the other one largely is independent of that and can just benefit from being further away from your resonator. And this is then maximized as we go to the control point where where both flux noise and the interaction with the resonator is minimal, giving us a very good T2 echo time. What suffers, though, is the T2 Ramsey time, and we understand this also very well. This is because of the media mode not being nicely into the transmon regime. So this will experience some charge noise. It will fluctuate a bit. It will immediately put that also to your qubit mode. This is, though, easily fixable in the later designs. Now we can put this mode also in the transmon regime, and we get rid also of this diminishing part. But we still get very nice performance even in this effect. Okay, so this should have been coming up, but exactly that's what I've been saying. So T2 is limited by charge noise, and there's still, of course, the remaining challenge that we need to we need to design the tunability of the mediator mode, and we need to deal with a somewhat larger footprint. Okay, coming to the outlook and our current experiments, and there I also want to refer to Frederick's paper. If you want to go more in depth, what we're now, of course, trying to do is not only couple to readout elements, but we want to use this also to build scalable architectures, and now we are testing what we can do with coupled qubits. And so we can immediately observe the same effect. So if we test, for instance, the ZZ interaction, if we couple the qubits like that, you can see that this is vastly diminished. So we are here below 5 kilohertz, virtually on any point of this tunability range of the 1 qubit. And what now emerges is actually, so this I can only glance over a little bit. What now emerges is a state-dependent transition spectrum of the mediator modes, and this we can use to do now geometric C-phase gates. So now by off-resonantly driving some of these transitions here, and of course taking care that in all cases we don't lose population to the mediator modes, we can implement a 2-qubit gate, and this we are in the first iteration of this, we are already getting above 99% of 2-qubit gate error. But I think the more convincing argument here is the high on-off ratio. So it's really, really nice to get rid of the interactions of the qubits if you don't want to have any. Good. With that, I'm also at the end of the talk, and then here's the summary, and then I hope there's some questions. This is our group, and thank you.
Thanks for this fantastic talk, Max. Yeah, we have time for quite a few questions. So,
hi, Max. Thanks for the great talk. I had a question about the way that you couple between two Pimon qubits. Yep. Does the you want to couple between the two mediating modes. Do spurious couplings to the other modes affect the performance of the device, or does it impose like a specific kind of like design orientation on how you have to couple these modes? Because maybe the breathing mode has a certain like dipolar moment to it that you have to couple to capacitively to suppress other couplings, or?
So far it's just 2 qubits, really just coupled capacitively. Now we are checking if we can do gate schemes, but this will definitely be a concern, yeah. So of course we need to make this then scalable. The nice thing is you have a conditional emergence of this where you have to like resonantly put the mediator modes at the same point. Okay. So then only you get this level spectrum, and then you can really pick 2 qubits that should do that, even if you have more coupled to this node. Potentially, this we didn't test yet, of course.
Great, thanks.
Just behind you, Chris. Yeah.
Thanks for a nice talk. I wanted to know about the speed at which you should drive through this transition with the flux pulse that you show. I'm thinking like non-adiabatically, adiabatically, and like transitions and so on.
Yeah, A really good question, actually. So due to the direct interaction that we still have, there's of course a hybridization, and we need to, so if we go from the control point to the readout point, this is a good concern. So we need to really move there, watch out that we don't lose the population into the mediator mode, and then move further to the readout point. So you can do that very fast, so that doesn't happen, or you just wait for it to return. Basically, it's a coherent exchange in the end. So if you time it correctly, you go there, you wait for it to do a full operator, and you can move it without losing anything to the readout point. We also tested actually a couple of things where you move it completely to the mediator mode and then read out the mediator mode. That works as well. So there's interesting things that you can do with that as well. But I think in the final version, we are trying to go with the design that does not have direct coupling, and then you would really not have any photon loss into the mediator mode at all.
Thanks.
More questions, maybe in the back there. Let's just, fantastic.
Thank you. Maybe a related question. How sensitive is this design to asymmetry of the junctions?
Good question. I don't have it in mind. So the direct coupling is not entirely by design, but I cannot now tell you how large the delta is for the capacitances, for instance. Sorry, but maybe you can talk to Frederick in the poster session. I'm sure he knows.
Let's maybe do one next and then the one in the front.
Hey, thanks for the great talk. I was wondering about the randomized benchmarking experiment. It seems like your single qubit gates are single qubit gate errors.
Yeah, so it turns out there's a couple of TLS floating around that make us barely kind of use this qubit. It's also not entirely at the protected point, so just the performance of the individual qubits is not super great in this particular chip. So we are hoping that solves itself, that we can do this completely, but yeah, you're right, there's definitely single qubit issues, yeah.
So the coherence times wasn't that great on this device?
Yeah, exactly, especially on the points that we need to go for the 2-qubit gate, yeah.
Thank you.
Okay, then let's do the question in the second row.
Hello. It's working.
Yep.
Thank you very much for the interesting talk. I don't know if you could elaborate a bit more regarding this thermal population in the resonator. How do you characterize it?
How do you characterize it? We basically have a noise source. We basically put an amplifier with white noise on the room temperature stage, and we crank it, and then you have a rising noise floor that's just white, and it will populate your resonator.
It's not like you go to a thermal photon granularity or?
Oh, it's really simple. You just put more amplification of noise on your room temperature. You get a rising noise floor. You get population in your resonator. That's a very simple experiment, yeah.
Yeah, thank you.
We have time for one or two more questions. Chris again, yeah.
I'm very curious about this high-frequency internal mode that you have that you kind of neglect in it. What frequency does it normally sit at?
I think above 20 gigahertz.
Okay.
We can't even actually spectroscopically see it because it's so far away. Yeah.
Okay, that solves my follow-up question then.
Yeah.
One last question. I had a question, actually.
Okay.
So you're moving most of your control scheme so entirely towards flux. Do you expect, if you have other coupling schemes, that, how do you think about the scaling and the ratio between microwave and flux biasing?
Yeah, so I wouldn't say we move it completely. It's definitely an interesting candidate. So it's also not unique to the fluxonium. That's also interesting. So the subharmonic driving works also on transmons. For the fluxonium, it gives a nice benefit that you can, instead of 2 lines, have 1, and that's definitely tangible. But yeah, we are of course putting this into a toolbox, and we have it in case we need it. For scaling, it helps. It's an option. Let's say it's not like now everything we do, I would say.
Wonderful. Then let's thank Max again and. All right, next up we have Simon Pedersen Fors from Chalmers University. And he will tell us about scalable and non-perturbative effective models for superconducting QPUs.
Let's see. Great. So hello everyone, and thanks for joining this talk on the topic of modeling whole arrays of superconducting qubits coupled together. I'm Simon Pettersson Fors, and as said, I'm a PhD student at Chalmers University of Technology, where I'm part of the modeling team, where we try to help our experimentalists in our local effort to try to realize and implement these kind of superconducting qubit processors. And I would like to thank the organizers for giving me this opportunity to really speak about a topic that's close to my heart and I'm deeply interested in, which are these scalable effective models for superconducting qubit processors via the continuous unitary transformations. Now let me break down this title for you. So scalable effective models refer here to models we can use to try to model systems in the range of hundreds of coupled transmons or other types of qubits. And continuous unitary transformations is the method we have been exploring to try to realize these kinds of models. So what I would like to do here today is to share with you some results from this exploration. And what I'm very happy to say is that we have in this project now reached a point where we managed to simulate the energy spectrum of up to and around 100 coupled transmons. So we'll come to those results later, but I'm really happy about that. But when we get there, let's try to start off on maybe some more common ground, and that is that it's freaking hard to simulate this system. It's part of the reason why we're trying to build a quantum computer. And the reason for that is what I would like to call this kind of a curse of dimensionality, is that when we're trying to describe these systems, there are many body quantum states that are described by these kind of amplitudes, which are tensors in the different subspace systems. And these amplitudes, as many of you probably know, are exponentially large in the system size. N here is the number of qubits. Luckily for us that's trying to simulate the systems is that there are some remedies proposed. For instance, maybe the most well-known examples are tensor networks, where we had this kind of matrix product states represented here, where we can break down these kind of tensor structures in more low-rank structures to try to simulate this. And the reason for why this is working is that these matrix product states are not exponential in memory, but they are linearly in memory in the system size, with some cost of this kind of a bond dimension, which is the dimension of these bonds. And we had some really nice work here from the group at Google lately, where they showed that with this kind of a matrix product states method, they are able to simulate the energy spectrums of a coupled transmons array at least up to 25 qubits with 40 couplers. And my motivation in this work is not really to try to replace the different tensor networks. It's rather we've been following a different line of thinking. And here we think there's a room for more than one method that can benefit from it. So rather the line that we're thinking is more in line with this kind of effective modeling and more renormalization theory. So the question that we are asking ourselves is more of this: is there a more efficient model? Like from the circuit, we get this kind of circuit models, but there's many degrees of freedoms here that are getting wasted in this description. And we just want to use the most important ones and try then to integrate these degrees of freedoms out. And the key idea here is that all these couplings are not equal. We want to remove the non-important coupling and keep what's important. And in this kind of a renormalization framework that we would be thinking about, we're thinking that we want some kind of a renormalization transformation that takes us from this circuit Hamiltonian to some more effective description. And then we want some kind of update differential equation, which takes us from the initial parameters to some more effective parameters here. And important here is that the effective model and the circuit model needs to give the same results for the relevant observables that we're considering. So for instance, the energy spectrums in the systems, or long-range couplings, or whatever we're interested in about here to try to describe in our experiments. The different effective models we could consider are, we might want to integrate out the couplers, we maybe just want to express the low energy physics of our system, or we might want to find maybe some block diagonal or fully diagonal model where we can extract the observables that we want. And within this kind of a renormalization group frameworks, we have a bunch of different methods. But as I hinted at before, the one we've been exploring are these kind of a continuous unitary transformations that have been independently developed in previous works. So to give you a quick brief introductions into continuous unitary transformations, probably the more well-known transformation you might know about is the Schrieffer-Wolff transformation, where the idea is that we start off from some circuit model, let's say, and we try to transform to a more diagonal model by perturbatively taking care of the couplings in the model. And the idea for the continuous unit transformations are very similar. But what we add here is that we want to do this kind of infinitesimal expansions instead, where the Schrieffer-Wolff expansion is now exact instead of we're neglecting these terms here. And what this leads to is this kind of flow equations that we were looking for, that I told you before defines our renormalization flow here. And just for the sake of this talk, it's enough to think about this method as just a continuous version of the Schrieffer-Wolff transformation. There are, of course, more details, but just to have what to have in mind, what picture to see, it's enough to just think about it as a continuous Schrieffer-Wolff transformation. So to give you a quick example of how applying this method would look, let's consider Let's consider just a minimal example of a free transpond system. So we have let's say two transponds connected with some tunable coupler. We would start at some initial point. Here I'm going for diagonalization. So we're eliminating the couplings. Here we have the frequencies of the system. Here we have the couplings. And then by applying the methods, we can continuously remove first the couplings between the qubit and the coupler. We then renormalize towards some other kind of effective models where all the coupling is now between the direct two qubits. And then continuing the flow, we remove all the couplings, and we can see how the frequencies now converge towards the exact frequencies of the system. And what's actually then really cool about this is that we can then describe these large and larger systems, just showing you some results from just benchmarking with different kind of implementations. First two ones here are on my laptop, just using my CPU. But what's really great with this method is it's very much prepared for GPU acceleration. So here we, using different kinds of GPUs, all the way up to an H100, we here can now manage to do systems in the ranges of more than 100 qubits to compute this. And what's the secret sauce? Why does this work? Like, how do we break this kind of a curse of dimensionality here? And the reason for this is that if we have this kind of a few interactions models, the number of parameters is actually polynomial. It's not an exponential amount of parameters we need to describe these systems. And what it turns out is that these kind of commutators we need to evaluate as a consequence will be polynomial in size to evaluate. So we have here some way shortcutted away from this kind of a Hilbert space, and we're now working in a different space to do that. This has been pointed out before for fermions, but we're now doing it for our more bosonic models for our superconducting quantum processors. So to show you just some proof of concept and just some preliminary applications that we're looking into, one of the things I'm looking at here is that I want to consider the array, and I want to think about the different Z-Z couplings between all my blue qubits here between each other. So I have an array of 25 qubits with 40 tunable couplers. And zooming in just on the middle qubit, we can here compute all the Z-Z couplings in this array from this method. And this I do on my laptop. So this array here is efficient enough to just run on my laptop, which I'm very happy about, as you might expect. And the things we can realize here is that we have in red, we have the positive strength, the negative strength on the Z-Z coupling. And we can look at both the next nearest neighbors, but also more longer range couplings. And we can see this kind of exponential decay in the array of how strong these couplings are. So this we can then input into our design, of our processor, and try to think about the next generation, how we improve on this. So let me wrap this up with the conclusions. So I want to share with you that this continuous unitary transformation is a scalable way to achieve this effective Hamiltonians. These flow equations that then are working in the space of the parameter tensors, they are polynomial in the numerical scaling, which means that we can achieve this kind of energy computations, even up to 100 transmons in these coupled arrays. We're working on a manuscript here, so there will be more details coming up, but this is just a little bit of a glance and a preview of what we're doing. Having said that, I want to thank you for your attention and happy to take questions and chat more afterwards if you have any more questions on that. Thank you.
Thanks for the great talk, Simon. Where is the microphone? Yeah. All right. There's a question over here.
Great talk. You're using a lot of vocabulary that's very similar. I mean, you also mentioned Glasek and Wilson. So can I see this as a modern take on this flow equation method by Wegner and Kerein?
Yeah.
You look into that?
Exactly.
And do you also aim at looking at like strong coupling fixed points and strong renormalization? You know, if you have a weak effect on thousands of qubits, the aggregate effect may be big. So.
Good question. Yeah, it's building on top of this kind of a flow equation framework by the people that you mentioned. Okay. Some couple of references on the slides to these people, which are great works. And yeah, that's applications. A question of thinking about going into different kind of strong regimes, trying to see how the couplings will spread out on our device, for instance. So that's definitely example.
Maybe I shamelessly self-advertise a preprint of Chasseur, Kerein, and myself, where we do this in the context of adiabatic quantum computing.
Very well.
Okay.
More questions? Yes, over here.
Oh.
This is going to work. Thanks for the great talk. So I was just wondering, quantitatively, how much difference do you see in the results you get from this continuous unitary transformation approach to, for instance, like Schrieffer-Wolff? So, like, how much difference would you get in the prediction of a dispersive shift, for instance? Or
good question. So the thing with the Schrieffer-Wolff transformation is mainly we can only describe when we are in dispersive or perturbative regime. And the thing with this method is that we're moving away from that. We can also go into this perturbative strong regimes to try to describe it. So as far as the Schrieffer-Wolff transformation would be exact, this yields the same results. And when I would compare this to more exact organization methods for small systems, this offers more than the experimental precision that we're having. So you can see that this kind of like generalizes what you can do with Schrieffer-Wolff transformation rather than they are two different things.
I see. Thank you.
All right. I have one question because you're saying here 100 coupled qubits. Yep. I'm of course wondering, is this scalable beyond, or do you think you're like hitting any limits there?
So what is limited by is right now it's the memory of the GPUs. That's one point. So you can switch to more memory-heavy CPU clusters to run larger and larger systems. So like this kind of 144 transmon is not the limit. We can go beyond that. Then how far you can go depends on how much precision you want in your computation. So there's a balance here between what kind of interactions, what kind of couplings we're approximating, and how big system we can consider. So there's many trade-offs to do here when running these simulations.
Wonderful. Let's thank Simon again. Mm-hmm. All right. right, and now we have the last speaker of this session, which is Verena Vollner from FAU, and she's going to tell us about multi-qubit couplers and multi-qubit gates.
Okay, so yeah, thank you for the organizers for this amazing conference and for giving me the chance to present our work. And since it's like right before lunch, I will present our recipe for multi-qubit couplers and also how to get multi-qubit gates. So as we have seen before, like also in the two talks before, up to now, people use this rectangular grids with qubits with 2-qubit couplers in between. Because it's very nice for the surface code. Now, our proposal is, okay, we keep this rectangular grid, but instead of having only like these 4 2-qubit couplers in between, we have 1 multi-qubit coupler. And now this gives a huge advantage when you want to scale up, because for already you see for 4 qubits, you need 4 couplers versus 1. And then when you go to a 9x9 grid, you have 12 2-qubit couplers, but only 4 multi-qubit couplers. And then you can also calculate this if you want to go even higher, where m and n are the number of qubits in a row and column of this qubit grid. And then by having this coupler in between all of these 4 qubits, you can have a very high connectivity. So you have all-to-all connectivity, because you can do gates between like all the horizontal qubits, all the vertical ordered qubits, and also over the diagonal, which also reduces the number of gates you might require, because, for example, here, if you want to do a gate over the diagonal of this plaquette, you would need a few I-swap gates or swap gates, for example. But we can do it directly via this one coupler. And because we not only have a coupler between 2 qubits, but 4, we can have gates between several of these qubits, so also 3 or 4 qubits. So the first ingredient for my recipe are the couplers. So we looked at 2 different choices for the coupler in the middle. The qubits are all transmons, which are capacitively coupled to this coupler. And for one, so we look at a squid, which has a time-dependent external flux pump, and also a snail. But first, let me go to my second ingredient, which is parametric driving. Because we have these 4 qubits and only 1 coupler in between, so we need to prepare gates that only trigger the interactions we want. So if we want to have a gate between qubit 1 and 3, we don't want to have a gate between qubit 1 and 2, for example. So we go to a parametric driving scheme, and all of our qubits have different frequencies, so all the detunings are different. And now we can drive the coupler with some external pulse that has a DC part and a time-dependent part, where the time-dependent part is some amplitude times a cosine modulation of the drive frequency. And now, via this parametric driving scheme, we can really trigger the interactions we want. So we can, for example, have the interaction between 1 and 3, 1 and 4, 1 and 2, and so on. And to analyze this a bit more, because I mean, also we are a theory group, we want to get to know what happens. We did like this extended Fourier transformation, which is called Jacobi-Unger transformation. And here for the snail potential, I just wrote it down as an example. Then you get some cosine phi and sine phi terms, which then are multiplied by these, I call them F terms. And these F terms are Bessel functions of the first kind, of the 0th, first, and second order. And here you can already see, okay, if I want to have an even-powered interaction, so for example a 2-qubit or 4-qubit gate, I have the term cosine 2 omega d, but if I have a sine interaction, so for example a 3-qubit gate, I have the cosine omega dt. This means if I want to drive for a 2-qubit gate, I need to drive with half the difference frequency. And the Bessel function terms are also very nice to analyze at what frequency, at what amplitudes I might need to drive my gate to get the best outcome. So back to the first ingredient, the couplers. So this is the Hamiltonian for my general system. This also looks the same for the snail. So we have the 4 transmon Hamiltonians, we have a coupling term, and we have the time-dependent snail term, and now you might the time-dependent squid term, and now you might wondering why we have this 1/2. I told you we have a time-dependent driving, so we need to consider the irrotational gauge. And since for the squid we have 2 junctions that are of the same value, we get 1/2 there. And for the snail, this is the same. In generally, a snail can have n big junctions and this 1 small junctions times the symmetry parameter. But in most of the literature, they use 3 junctions, so we also used 3 junctions. And here, this irrotational gauge is a bit more complicated because it consists of the capacitances of the left leg and the right leg. Now, in most of the literature, the snail, this asymmetry parameter alpha is given to be like around 1/3. But like people use this because they want to suppress the quartic term, but want to really enhance the cubic term. But to get like this phi squared, for example, which is beneficial for having 2 qubit interactions, this is not the best regime. So what we did is we plotted the prefactors at the minimum of the flux, and did a parameter search dependent on alpha and phi DC to see, okay, how do we need to choose our like fixed parameter alpha and the phi DC value for getting the best gates. And here you can always see like the absolute of the cubic over the quadratic component, the quartic over the quadratic component, and the quartic over the qubit component. And for example, for a 2-qubit gate, you want to have this here small, because you want to have a dominant quadratic component, so you need to be in the blue area. But you also want to have this here small, so you also want to be in the blue area. So for example, this here might be good, but you can even get a better value if you are here, so around alpha equals 1 and phi DC equals 0. And then for the 3-qubit gate, you can do the other way. So here you need to be in a very reddish, orangish area, and here you need to be in a bluish area. And like, if you're wondering what these Wien rate points are, these are where the numerical root finding of the minimum didn't find any values. So like there we didn't find anything. So our proposal is we don't keep the normal snail, but we make it tunable. So instead of like this fixed alpha junction, we say, okay, we put a phi DC, we put a squid here, which both junctions had the original EJ but half, and we can pump it via DC flux. And we made this here a bit longer, so there's no flux crosstalk. But we can still pump this loop via this external time-dependent flux. Then, as I said, we want to do 2-qubit gates, for example. And here, the problem is, like, if you have two qubit couplers, you only mostly look at the subsystem of the 2 qubits and the coupler. But here we have a system where there are already 4 qubits coupled and hybridized with each other. So we need to consider like the 4-qubit Hilbert space, where, for example, if we want to have a gate between 1 and 2, we need to tensor it with the identity on 3 and 4. And then the fidelity gets calculated by this because we get a 16 by 16 matrix. But to compare it to like 2-qubit coupling architectures or also experiments where the 2-qubit fidelity is measured, we trace out the spectator qubits to get a reduced 2-qubit fidelity. And then we did some rudimentary pulse optimization of a super Gaussian pulse, which looks like this. And yeah, these are the results. So I did 3 examples here. One is the horizontal, a gate between horizontal qubits, a gate between diagonal qubits, and a gate between vertical qubits. And as I told you before, we saw that you need to drive your even terms with half the difference frequency. So here we need to drive with omega-1 minus omega-2 half, for example. And I get these fidelities for the 4-qubit fidelity, and this fidelity for the reduced, so the traced out fidelity. And you might wondering why there are so many lines in there. The thing is, like, the gate doesn't even needs to work if we have all the qubits in 0 except, like, for example, the 1 in this case, but it also needs to work if the spectators are excited, of course. So we plotted all the trajectories of all the possible states the gate can be in here. And we did the same for the snail. So you can see even the fidelities here are even a bit better. Here we chose the, like you have seen maybe in the plot, we chose a really bluish value, so the alpha is around 1 and phi DC is 0. And here you can also see some problems which might impact the fidelity already, because some of the frequency differences, if one of the spectators is excited, we don't get the really right difference frequency. And then I also promised you that we have the possibility to do multi-qubit gates because of our architecture. And here I brought 2 examples. The left one is done with a snail, because only the snail of our 2 options has a term where you can have odd powers. And the right one is done with a DC squid, but you could also have a 4-qubit interaction with a snail, because you also have a 4-qubit term there. And so these are not gates that you know, or you would say, okay, this is an Eid-Hoffoli gate, for example. But these are the native interaction as we have them in the Hamiltonian, because I can analyze this very long Hamiltonian and see, okay, now I need to drive with this frequency to get this interaction, for example. But of course, you can write this with sigma matrices to the time evolution, and then you can get a matrix and decompose it into several known gates. And yeah, so here you see we don't have to drive with half the frequency because we have an odd powered interaction. So we have a phi to the 3 interaction, namely A1, A2 dagger, A3 dagger plus the Hermitian conjugate. And here again, because we have an even interaction, we need to drive with the half frequency. So to summarize, we can do multi-qubit couplers by doing a squid or a tunable snail as the coupler. But it's important that we need to select what gate we want to do. So we use a parametric driving scheme, so all our qubits are mutually detuned. And by this, we can achieve an all-to-all connectivity, so we don't need to have like some strange gate in between or other couplers. We can get gates between all the qubits. And it's also possible to have some multi-qubit gates. And with this, I want to thank my supervisor, Michael Hartmann, and my collaborators, Stefan Tasler, Lukas Heunisch, and Marcan Fani. And this is in preparation at the moment and will soon be on archive.
Thank you much, Verena. We have time for a few questions. I'm looking for the microphone cube again. It's over here. Maybe I start then. I'm trying to figure out still what are the trade-offs of going with a squid or with a snail design.
Okay, so the squid, you don't have this 3-body interaction. So if you say, oh, I don't need the 3 qubit gates, you could also go with a squid, for example. And then, because first of all, I think it's easier because you only have the 2 junctions instead of the 3. Or if you say we even have our tunable snail, you even have 2 more junctions instead of the 1 alpha junction. But I think the coupling mechanism is more or less the same. So it just depends on if you want to have this extra nonlinearity of the snail.
Yes, a question here at the very end.
Oh.
Casper will survive, don't worry.
Thank you. So the terms you showed for the multi-body couplings, they didn't look like they are conserving the energy. Could you maybe comment on this? What's happening there?
I mean, I just showed one part of it because you always have the emission conjugate. So you have, for example, A1 dagger, A2, A3 plus A1, A2 dagger, A3 dagger.
And what happens to the coupler there? So did you get somehow rid of this by some elimination or?
So the coupler always approximately stays in the ground state. It just like jiggles a bit by driving around like this with this parametric driving.
How did you eliminate it from the Hamiltonian?
No, I just mean like for this, the coupler doesn't really like change its energy levels. It mostly stays in its ground state.
Okay.
But I need the coupler because like the modes hybridize quite a lot, and by this hybridization with the coupler mode, you get this coupling terms that now are time dependent. And then by going to the interaction frame and driving with the right frequency, you can really facilitate the interactions you want to have.
Yes, another question up there, and then at the center. Yeah.
Thank you for the talk. I wanted to ask about the plot you showed with the parameters of the snail. We saw there were these red regions where you could not find the parameters of the snail. I was wondering whether it's related to the regions where we have multiple minima in the snail potential. Yeah.
Yeah, so this was, I would say, for us to visualize what parameters might be good. And of course, the snail can have multiple minima for some parameters. So I think most of those wine red dots are where there are multiple minima. And then I did this plot with Mathematica. Then the Mathematica says, oh, no minimum has been found. I need to see if I can say, oh, if there's one, just take like one of it. But we could already see or like gain some information from this plot. So for now, I just use this.
Yeah, so the rest of the points can still have multiple minima.
Okay, then one last question that was right.
So there was a talk earlier this week where they had some, also like 6-qubit with some resonator, and then they said that the trade-off was that they didn't have any parallelization between all the qubits coupled to the same mode. Would you guys have the same issues, or can you drive the coupler in some way where you drive parallel gates at the same time?
So we can drive parallel gates at the same time. But there might be like some fidelity trade-offs. So we did some analysis where we did a two-tone pulse because we have 2 gates, for example. And there you need the two drive frequencies. But I think like even there the optimization is a bit more tedious. But in principle, it's possible because the coupler can be driven with these 2 tones, and then you can get 2 gates in parallel.
Thank you.
Great. Let's thank all the speakers, so Max, Simon, and Verena again, and everybody have a great lunch.
Great, thank you. And then now we will move on to the lunch and the workshops. For that, Amber has some practical information.
Thank you, Christian. I will also have one slide, I think, to show the rest of the program, including the lunch. Otherwise, I just explain you. So as just like yesterday, 12:30, the lunch is served here. There are 3 lines you can join. You can take your lunch and eat it in the venue. You can also use the booth space in the back of the venue. And you can also go outside to the SQA summer terrace. If you take your food just like yesterday, maybe for the people that just arrived today, don't forget to take back your cups, mugs, and plates and cutlery to the venue. And then I think, well, the rest of, after lunch, there will be in parallel poster sessions and workshops. So the first, there you go. First 2 workshops will be the one by Q Tindu in Pathé and one by Orange QS. Afterwards, there will be 2 more workshops, 1 hour later, one by Controlox and one by Quantware. For the people that are new here today and didn't follow any workshops yesterday, the Pathé is the cinema right next door. So you go out of the venue to the right, and then just through the front entrance, there's a special gate for SQA attendees that you can just walk through. And just like Quantum Machines offered popcorn yesterday, Orange QS is also offering popcorn. We get inspired by each other. And it's okay to steal good ideas from each other, right? Then for the posters, they will again be here on stage to get a backstage look into the science. Take care when you enter the stage for the small stairs in front. And then I think that's about it. Later about the dinner, which will be in the Nieuwe Kerk this evening, we will share some more information after the next keynote and scientific sessions. That's it.
Maybe one thing, if you didn't sign up for the dinner, you can still join. Everybody that are here can join, as long as you have a badge. about his work, or the work at Amazon, on hardware-efficient error correction using concatenated bosonic codes. So please welcome Harry to the stage.
Sweet. Everyone can hear me in the back? Cool. Yeah, so my name is Harry Putterman. I'm from the AWS Center for Quantum Computing. And I'll be telling you about hardware-efficient quantum error correction using concatenated bosonic qubits. And that maybe sounds like a bit of a mouthful, but hopefully by the end of the talk, you'll understand what that means. And it's maybe the question is supposed to be at the end, but if I don't want people getting lost, so if there's questions in the middle, you can holler out at me and I'll like repeat them so people online can hear and stuff. So don't hesitate to just interrupt and ask questions, though that might be against what's supposed to happen. Sweet. Yeah, so this is our actual quantum chip shown right here, and all good quantum chips need to have a name. So we call ours Ocelot, and it's a bit of a play on words. It sounds like oscillator a bit, which maybe is alluding to that we're doing bosonic qubits, and it's also a type of cat, and so maybe it's a cat qubit and bosonic qubit, so it's a sort of nice allusion to what we're doing. Sweet. Yeah, so what is the AWS Center for Quantum Computing? We're a research center located on the Caltech campus, and we work on super quantum computers. And we have the aim of making fault-tolerant quantum computers. And we're led by Professor Oscar Painter and Fernando Brandão. And this talk will be based on these two papers shown right here. And I'll give you like a very high level of these, but we maybe uncharacteristically for an industrial effort gave very much technical detail about what we did. So please look if you're wanting to see more detail or ask me. Yeah, so this has been mentioned many times, but what does it look like to get from where we are now to useful quantum computers? Right now, we have, say, tens to hundreds of physical qubits with error rates of 10 to the -3, and we need hundreds to thousands of good logical qubits, which means error rates of, say, 10 to the -10 or even lower. And so, it's a bit finicky. There's this very big chasm between where we are right now and what we have to get to, and the error correction is a means that we can sort of cross this very big divide between where we are now and where we want to get. And so before talking about quantum error correction, because it'll be sort of a helpful allusion to what we're doing, let's talk about classical error correction. In that situation, we have one bit we want to protect, which has only two states, 0 and 1. And these physical classical bits could be subject to bit flip errors, which are transitions between 1 and 0 and 0 and 1. And, they have some characteristic probability px of happening. If we want to protect this information, we can encode a logical classical bit into a string of physical classical bits. In this, for example, here with a repetition code, 0 into some string of 7 zeros and 1 into some string of 7 ones. If there's some errors on the system, for example, here, a couple of the bits happen to flip from 0 to 1, then we have like these errors shown in red right here. And then it's very simple to do error correction here. We would just do some majority voting. In this case, there's more zeros than 1, so we decode and get 0. And in this case, there's more 1s and 0s, so we decode and get 1. And so it's very simple to do the error correction in this setting. And as long as there's fewer number of errors than roughly, as long as less than half of the bits flip, we'll be OK and we'll protect the bit. The situation with qubits, as we all know, is much more complicated. We have this, three-dimensional block sphere, and not just the 0 and 1 states. We could have, for example, equatorial states plus and minus. And we typically realize these qubits, as has been discussed in many talks today, using like a transmon, for example. We have like 2 energy levels of an anharmonic oscillator, or some Rydberg atom, and we have like some hyperfine transition representing our atom. So it's really just 2 energy levels of some physical element. Yeah. And so what is one of the reasons that performing quantum error correction is harder is that qubits have more than one type of noise. They do have bit flip noise, like classical bits, this 0 to 1 transition, but they also have phase flip errors taking us across the equator from plus to minus or minus to plus. And so there's a sort of increased number of errors we have to correct for, or a type of error we have to correct for. And that's just one of many complications, I would say. And what that means, yeah, and so we want to do some sort of error correction here. And it's going to be more complicated in the classical case. We can't just use a simple repetition code. And so schematically, it looks the same, but we have many physical qubits. We put them together with some quantum error correction protocol to get some logical qubit. And hopefully, this logical qubit has lower error indicated sort of schematically by these arrows than these individual physical qubits. But this ends up being much more complex. We can't just use a repetition code. If we use a repetition code here, we'd protect against bit flip errors, and then we have tons of phase flip errors just bleeding through, and we wouldn't get any benefit. So it becomes more complex in the case of classical error correction. Makes sense, everyone? Cool. Sorry, this thing is kind of finicky. Yeah, and so this is a very active field, of course. There's experiments going on in trapped ions, superqubits, neutral atoms, on and on and on. And we've heard about many of them, like from Nathan, as just one of many instances this week. And so this is like the sort of a very active direction. This is what we've been thinking about. And typically how this looks, Nathan gave a different example, so maybe this didn't line up so well, but most often people are working with this surface code. So this is a two-dimensional grid of physical qubits, and the details don't matter so much except that each of these circles here is a physical qubit, like a transmon, and we have a two-dimensional grid of these qubits. And what you should think about is that one dimension corresponds to protection against X or bit flip errors, and the other dimension protection against Z or phase flip errors. And we're encoding this logical qubit into this two-dimensional grid of physical qubits. But this has increased complexity to the classical case I just showed with the repetition code. For example, quadratic scaling of distance, which is like the minimum number of errors you can correct. So like the number of qubits you need to get a certain distance grows quadratically. So there's just increased complexity even on that level. And then decoding becomes more complicated because there's more types of errors you can have. So it's just strictly a more complicated setting than the classical case. I realize I shouldn't be standing in the corner there. Sweet. Yeah, and so if you just ballpark the numbers, you don't have to go through it. I have here though, and you roughly typically get that in order to do useful things, you need millions of qubits. So you potentially need millions of physical qubits, and to me, and this is quite daunting. Some people are just like, oh, we're just gonna do it, but to me, this is quite scary. And so what we're working on is something, can we do something more efficient? And what we work with is sort of more novel kind of system, and so also maybe it's not the direct corporate interest, but can we also do some interesting physics along the way? And so that's really what we're talking about today. Sweet. Yeah, so now we'll talk about bosonic qubits and cat qubits, which are the specific type of bosonic qubit that we use. So as I showed before, standard quantum error correction, you have a bunch of physical qubits, you put them together with some quantum error correction to get some logical qubit. That's sort of this typical thing that's been done, for example, with the surface code. And we'll be using our sort of building block will be bosonic quantum error correction. So instead of physical qubits, we'll have a physical oscillator. So it could be like a electromagnetic resonator. You can think of like a quantum version of a simple harmonic oscillator. And this is a quantum mechanical object, and it has different levels and an infinite number of levels. For example, this level corresponds to 0 photons, 1 photons, 2 photons, 3 photons, etc. And it's a quantum mechanical object, so it can simultaneously be in like a superposition of 0, 1, 2, 3, etc. onto infinity. And so we encode information distributed across these levels with quantum error correction, but what we call bosonic quantum error correction. So we again realize some bosonic, a logical qubit corresponding to this oscillator, which we call a bosonic qubit. And this bosonic qubit hopefully has errors that are suppressed in some way compared to the physical oscillator. The physical oscillator might have loss, and hopefully this bosonic qubit, for example, is protected against loss or dephasing, or as we'll see later, it depends on the specific implementation. Make sense? Cool. Yeah, so there's many types of bosonic qubits, cat codes, binomial codes, GKP codes. These are all just different prescriptions of how do I assign logical 0 to some state, some superposition in this oscillator mode. And there's been very many exciting experiments correcting or suppressing physical errors with just like single bosonic modes. For example, like GKP break-even experiments. So this is a very active area of research, and it's maybe particularly going on in super qubits, where we're using electromagnetic resonators, 2D and 3D resonators. Yeah, and the question we have is, can we scale up the bosonic quantum error correction and realize improve hardware efficiency? Just taking these single bosonic modes, it might be unlikely that we'll just get one oscillator and get a logical qubit. That's maybe a bit unlikely, but what we hope is that we can put together many of these bosonic qubits. So we replaced this simple picture before we had many physical qubits with some quantum error correction protocol. Now we have bosonic qubits, each with their own bosonic quantum error correction, and then we have an outer layer of error correction, which is maybe more analogous like a surface code, or in this case, well, we'll see what our specific case ends up being. We'll have some outer layer of quantum error correction to get a logical qubit. And our hope is that correcting some physical errors at the level of this bosonic quantum error correction makes this outer layer of quantum error correction more efficient. And so this is what we call concatenated. It's these two levels of quantum error correction. Make sense? Any questions? Okay. Yeah, don't hesitate to ask questions, even though it might be against the rules. Sweet. Yeah, and so what is our specific type of bosonic qubit? We're using cat qubits, and so we encode information in coherent states. So this is sort of a very common object in physics, but we label them as plus minus alpha here, where alpha is just a number describing the coherent state. And what it means is that if it's plus minus alpha, the mean photon number of the coherent state is alpha squared. So if you look at those levels I showed of the oscillator, what is the population each level? This is just like an example, like n alpha squared equals 4 coherent state, alpha equals 2. And you can see that this coherent state is mean photon number of 4, and there's some distribution of population across these levels of the oscillator. And you can see in these Wigner representations here, this is plus alpha and this is minus alpha. Yeah, and so I need to tell you now what's our specific prescription for how we encode information to these two states. And so here we're showing the Bloch sphere that we use for our cat qubits. So the 0 state will correspond to the plus alpha coherent state, the 1 state to the minus alpha coherent state, and then the equatorial states, plus and minus, correspond to the positive superposition, the negative superposition of the plus alpha and minus alpha coherent states. And we call these the even and odd cat states. And the reason we do that, and what this will become important later, is that if you look at this specific state, you'll see that it only has occupation on 0 photons, 2 photons, 4 photons, et cetera, only on the even Fock states. And similarly for this state, it only has occupation on the odd photon numbers. So these are the sort of equatorial states from our system. Does this make sense? Okay, sweet. Yeah. And so we can start thinking about what are the error mechanisms that will, like the error channels that will affect our cat qubit. So the first thing we'll see is that if we lose a photon, so it's very common in an oscillator, you have 10 photons, you lose a photon, you go to 9 photons. That's a very common error mechanism in an oscillator. And if we lose a photon, that will cause a phase slip error, taking us from minus to plus or plus to minus. And the reason for that is that if we have an even photon, like 10 photons, we lose when we go to 9, even to odd. And so losing a single photon causes a transition between an even state to an odd state, and similarly odd to even, which constitutes a phase slip. So what we can see is that the loss of a photon causes a phase slip. So this Z error rate or phase slip rate scales with the single photon loss rate, and then also the mean photon number. Because if you have 10 times as many photons, you're 10 times as likely to lose a photon. Makes sense? Sweet. And similarly, we can look at the bit flip errors, the probability going from alpha to minus alpha or vice versa. And what you'll see is that as we increase photon number, and this is experimental data here, we're looking at the 0 state and the 1 state, or alpha and minus alpha. As we increase the photon number, the separation between these states increases. And furthermore, if you just compute the overlap between the states is exponentially suppressed as we increase photon number. So just like you perform an integral across this phase space distribution of these two states. And what that means is that these bit flip error rates, going from 0 to 1 or 1 to 0, are exponentially suppressed with mean photon number. The exact functional form might depend on the error mechanism, but some local error mechanisms like single photon loss, dephasing, et cetera, you'll have bit flip rates that are exponentially suppressed with photon number. So just to summarize, we'll have this block sphere. The bit flip rates taking us from 0 to 1 and 1 to 0 are exponentially suppressed with photon number, whereas the phase flip rates taking us between these equatorial states, they only grow linearly with photon number. It's clear? Any questions? Okay, cool. This is important, so just if there's any questions, don't hesitate to ask. Okay, yeah, and so you can see that this might be interesting. At this point, what we can see is that our outer error correcting code only needs to catch Z errors. The bit flip errors are sort of natively suppressed by our cat qubits. And so this will be the sort of the key thing that will be used in our experiment. And so what are we going to do? Before I was showing you the surface code, and I told you that one dimension was corresponding to protection against X or bit flip errors, and the other one against Z or phase flip errors. Our cat qubits, they will natively suppress the bit flip errors, or if they're implemented properly, as we'll see later, which they are, they'll natively suppress the bit flip errors. And so what that means is that we need less redundancy for these X errors. If in the limit where we have no bit flip errors, why do we need this extra dimension to protect against bit flip errors? And so you can see I'm sort of fading this away here, and we'll actually operate in this very extreme limit of just a repetition code. So that's why at the beginning I started with this classical code, because that's actually the code we'll be using. We'll just be using a classical error correcting code to protect against Z or phase flip errors, and we have no protection against bit flip errors whatsoever. So this is realizing a variant of this repetition cat code proposal from Guyot and Mirahumi. Yeah, so it's a kind of extreme limit to be in, where we have literally no protection against bit flip errors. And so we're relying on the fact that our cat qubits themselves can suppress these bit flip errors. Makes sense? Cool. Yeah, and so how does it look to protect against the phase flip errors? The bit flip errors are natively suppressed. How does it look to protect against the phase flip errors? We're just doing the same, just to make an analogy before, we encode like our logical plus state of our logical qubit into some string of pluses here. And then there might be some phase flip error due to a single photon loss event on one of these storage modes. As I said before, like a single photon loss event can cause a phase flip. So imagine this one switches from plus to minus. We just measure joint parities indicated by these triangles. So what that means is this cat qubit in the same state as this one? Yes. Is this one in the same state as this one? No. And so then we'll get some flags here indicating that there's some joint parities that are inconsistent. And then we just, from these joint parities, we can just, as long as there's not too many errors, we can say, oh, the fact that these two are flagged means that there was an error here and we can correct it. So that's how the phase flip error correction works. It's very simple because we're just using repetition code. Okay, sweet. So now let's see the device that we're using. Yeah, so this is sort of a schematic of our device. And so we're doing a distance 5 repetition cat code. So we have 1, 2, 3, 4, 5 harmonic oscillators. And each of those harmonic oscillators is storing a cat qubit state. And then we have these triangles here are corresponding to these joint parity measurements I showed before, which more formally would be called stabilizer measurements, or stabilizers. And we actively measure these stabilizers to detect these phase flip errors like I showed in the last slide. So for each stabilizer, we have an ancilla qubit, and we'll be using transmons, and I'll show the detail of how this joint parity measurement works later. And then for each of the cat qubits, so each of these bosonic modes here shown in blue, that's where we're storing the cat qubit state non-locally across these infinite number of energy levels. So the cat qubit's actually stored in this oscillator. And each of those oscillators has a buffer mode, which, as we'll see later, is a way of actually realizing this cat qubit. And we're realizing, as I said before, up to distance 5. Makes sense? Okay. I feel like I'm fading into the shadows naturally when I'm talking. Sweet. And so just to reiterate what I said before, the bit flip errors are corrected, the phase flip errors are corrected by the repetition code. So for example, if you have a Z error here, it would be flagged by these 2 stabilizer measurements using these 2 ancillas. So you get these 2 flags. And the bit flip errors are natively suppressed by the cat qubits, so we have no protection against the bit flip errors. Sweet. And so how does our device actually look? This is we're using a 3D integrated device. There's 2 chips here. This top chip is an aluminum chip, which has all our junction elements, like our transmons and these buffer modes, which are these nonlinear elements that all need junctions. And then our bottom chip is a tantalum chip. And so, as you might know, with tantalum, you can get typically higher coherence. And we can use a very simple fab process because we only need linear elements of this bottom chip. There's no junctions. So we sort of have a multi-material stack going on here. So the harmonic oscillators, bosonic modes, or which I'll also refer to as storage modes interchangeably. Sorry that there's so many different terms. Those all live on this bottom tantalum chip. And so maybe uncharacteristically for one of these industrial efforts, here's actually a circuit representation for our device. So we have, as I said before, we have distance 5 repetition codes. So there's 1, 2, 3, 4, 5 resonators here. These are coplanar waveguide resonators that are the bosonic modes where we're storing our cat qubits. Then for each of these resonators, there's this green element here, which is the buffer mode and some associated circuitry. And so these are what we'll realize. We'll go into in more detail what these do in a second. And then between the two, between each pair of storage modes, or which hold the cat qubit state, we have the ancilla transmon, which is used for this joint parity measurement. So that's how the circuit looks. And our parameters, like this ancilla T ones, are pretty unremarkable, but the storage T ones for 2D resonators are quite good, especially considering, as we'll see later, a lot of the details that go into, I think they're among state of the art for these sort of integrated devices where we're doing 2-photon dissipation, which inherently, as we'll see, involves coupling to a highly lossy environment. Cool. Sweet. Yeah, so now we'll walk through some details of this. So let's focus on one of the cat qubits. So we have our harmonic oscillator coupled to a buffer mode. And we want to, as I said, have this cat qubit encoding, so this plus alpha state and this minus alpha state. And so you could start off in some situation where you have a nice, plus alpha coherent state, and then you naturally have all these sorts of errors that can happen on cat qubits. You have like our oscillators, dephasing, loss, undesired kernel errors, et cetera. And you could end up some messy state like this. And I don't have to convince you that this state is not going to have all these glorious bit flip suppression properties I showed you before. And so we need some stabilization mechanism that confines us to this plus alpha, minus alpha manifold. And maybe, how do we actually do that? That's sort of the non-trivial question here. And to explain this, maybe I'll make an analogy to a simpler case. Imagine we have one to stabilize a single coherent state. We just need single photon loss and a single photon drive represented by this, which is equivalent to this master equation right here. So if you have a simple pendulum or something and you're driving it and it has some damping, you'll get some steady state coherent state. That's all that's happening in this simple setting. And then you can kind of take a leap of faith with me that if I generalize this to 2-photon loss and a 2-photon drive, that will stabilize both coherent states. Well, then the question is, okay, sure, but then how do we do this? And this is sort of where the power of superconducting qubits comes in, that we can sort of engineer these highly, maybe non-trivial and nonlinear interactions. And so our stabilization is mediated by this buffer mode connected to the storage mode. And pairs of photons in the storage mode convert to a single photon in the buffer mode, and vice versa. And so this just continues to happen. But then we heavily damp this buffer mode. And by damping the buffer mode, what we do is that we 2 photons in the storage mode convert to a photon in the buffer mode, and then it decays the environment before it has time to convert back to pairs of photons in the storage mode. So that gives us an asymmetry, which allows us to realize a 2-photon loss. And then lastly, we'll add some little bit of intentional drive on this buffer mode, which gives us now a 2-photon drive on the storage mode. So we get this balance of 2-photon loss and 2-photon drive. And you can see experimentally, as we increase the buffer drive amplitude, this weak drive on the buffer, then we get this increased separation between the coherent states as we're adding more 2-photon drive while we're keeping the 2-photon loss rate fixed. And just think of it analogously to the sort of the simple case where you just have stabilizing a single coherent state with single photon loss and a single photon drive. Yeah. And so how does this look if we zoom in on one of these sections? We have our storage resonator. we have our buffer mode, and then we have this multi-pole filter here, which you can sort of think of as a way of giving per cell protection to the storage mode. And the cat qubit state, as I said before, is stored in this coplanar waveguide resonator right here. And this is, yeah. And there's many more details in our papers on the details. So there's a lot that goes into actually making this cat qubit work. And so I told you before we want this exponential suppression of bit flips and this only linearly, that we should expect the phase flips to scale linearly with photon number. Do we actually see that? And the answer is yes. So on the left here, I'm showing the bit flip time as a function of photon number. And note that this is a log scale here. So you can see that going from 1 to 3 to 4 photons, we have this exponential increase in bit flip time, starting at, say, already like quite good numbers at even a single photon here, like 500 microseconds, up to like, say, tens of milliseconds at alpha squared equals 4, with some differences depending on each of the cat qubits. And similarly, if you look at the phase flip rate, the phase flip time, so the inverse of that goes as 1 over alpha squared, which is exactly what we expect. And it turns out to be consistent with our storage T1. So if you look at like alpha squared 1, it's roughly comparable to like where we'd expect this to give. If you just read off the y-axis, you'd expect it to agree with storage T1, and you can see that indeed it roughly does compared to like 70 microseconds. And furthermore, this is all simultaneous. So all these cat qubits here are being stabilized simultaneously, and we still achieve this performance. So I guess my takeaway here is that cat qubits can be reliably manufactured once you sort of really understand the details of these superconducting circuits. Sweet. Cool. And then how does it look where our storage couples to our ancilla? So just zoom in on one of these stabilizers. The ancilla is a trans 1 qubit, and we use the first 3 levels. So we encode our information to the ground state and the second excited state. And I won't go into too many details here, but if you zoom in, you'll see you have our ancilla qubit here in yellow. And it's coupled to one storage mode on one side and one storage mode on the other side by means of, in green, these 2 tunable couplers here. And these tunable couplers allow us to toggle on and off the interaction between the ancilla qubit and each of the neighboring storage modes. And what's the nature of our coupling? So as I said before, it's a tunable coupling. We can turn on and off this coupling. And it's furthermore a dispersive coupling, which is maybe a bit more unusual in context of these tunable couplings. So it's a tunable dispersive coupling. And dispersive just means that the storage frequency depends on the ancilla state. And lastly, this is maybe more technical for the people in the audience that know, but it's also a chi-matched interaction, which means that the rotation rate of the storage mode is comparable when the ancilla is in its first excited state or its second excited state. And you can see here, for example, it's the canonical signature circuits of number splitting, and here it's sort of tunable. So whether the coupler's on or off, we do or don't have number splitting. Awesome. Yeah, so I'll probably only just briefly talk about our CNOT gates, but I just I'll mention it very briefly just because it's sort of the key challenge in the experiments, as we'll see right here. So as before, we have this distance 5 device here, and I showed you just now that we put in all this tons of effort to get exponentially suppressed bit flips. It's like not a trivial feat, I would say. But what could happen is, we have to do these joint parity measurements using these ancilla transmons. And these ancilla transmons are not as good as our cat qubits. They don't have this exponential bit flip suppression. And so if our ancilla transmon has like a decay error, this is a very common thing on transmons, T1, as we've heard about a lot today. This T1 error can then propagate to an error in our cat qubits and lead to a bit flip. So then all the effort that we put into making our cat qubits great is for nothing, because this ancilla error just propagates to an error on our cat qubit, and it doesn't matter how good our cat qubits are on their own. And so this is the key challenge in this experiment, is getting sort of a noise-biased CNOT gate. And it means that the CNOT gate must preserve some of this bit flip error suppression. I showed you have this exponential suppression of bit flips with photon number, and we have to preserve that when we do the error correction. And the error correction means just repeatedly doing these joint parity measurements. Yeah, and I won't go into details here for time reasons. But roughly speaking, it's all these ingredients I mentioned before. It's like they all come together in symbiosis between this like 3-level encoding, this chi-matching, this tunable dispersive coupling, our dissipative stabilization. All these ingredients come together to give us bit flip probabilities per error correction cycle of like 2 times 10 to the minus 3 levels. So it's not just the gate itself. You should think of this like for the full error correction cycle, everything that the cat qubit experiences is at this like 2e minus 3 level. Yeah, and I'll skip a few slides here just for time. I was expecting I wouldn't be able to get to that. Okay, sweet. So now let's discuss really the key thing in this experiment, which is the logical memory performance. And so there's sort of 2 parts to this. I showed that I sort of have to show 2 things to you, right? The first is that when we're doing all this repeated error correction with the repetition code, that the logical bit flip rate, which is what's induced by physical bit flips, is still suppressed. This means that all this stuff I said about the CNOT gate and the stabilization is actually working at the logic level. And the second thing is, how well are we actually detecting these faceless pairs? So I'll just reiterate this a few times going forward. So if you didn't quite get what I said just now, don't worry, because I'll go into this, repeat this many times. But just to say, there's sort of two aspects we have to check. And the first part we're going to be checking is how well can we correct phase slips with the repetition code. And so just to remind you, we have this distance 5 device. If we have like a Z or phase slip error here, it gets detected by these two neighboring stabilizers and flags them. And what we're checking here is how well are we doing this? How efficiently can we and accurately can we detect these phase slip errors and then correct them? And just so allude to earlier, where I was showing we had this encoding into some like string of pluses, for example, and if we have an error, we detect them with these joint parity measurements. This is what we're doing with this this aspect of correcting phase slip errors. And the sort of thing to keep in mind when you're looking at all the scales here are that uncorrected physical phase slips, or perhaps miscorrected is a better word, are the source of logical phase slips. So, yeah. And how does the circuit look? It's maybe a little bit different than typical error correction circuits. So it will look familiar, but then there'll be some key differences. So we have this distance 5 device, and now I've sort of oriented it the other way. And each error correction cycle looks like this, and I'll walk through it in detail. So we prepare our ancillas into this GF encoding, so the ground state of the transmon and its second excited state. That's what these gates here are doing. Then we perform 2 layers of CX or CNOT gates, shown here. And these are all, like each layer here is happening simultaneously. There's 1 layer and 2 layers. So there's 2 layers that are happening simultaneously. And each of these are these gates which have to be that, like that's sort of one of the hardest parts of the experiment is to make that these are noise biased. Then we map the storage modes, or sorry, I should say ancilla modes out of the GF superposition. And then lastly, we perform readout and reset of the transmon. This is what actually sort of extracts this information from the system. Here, the ancilla is getting entangled with the storage modes, and here we're actually sort of extracting information from the system. And while it's happening, sort of the unusual thing here is that we're applying this 2-photon stabilization on our cat qubits. And this is ensuring, you know, as I showed before, if we have like loss, curl, all these things, the cat qubit state will just get distorted. So we have to always be sort of, we're just like stroboscopically applying the stabilization to ensure the cat qubit stays confined to this plus alpha minus alpha manifold. So that's what these symbols here are showing. And it's sort of I would say it's maybe a bit departure from what you might expect. The sort of, that the stabilization is being, we call it like pulse stabilization, that we're applying it in this stroboscopic way. And that's sort of owing to the, that's not a trivial thing to do, and that's owing to the sort of the exceptional coherence over storage modes and like linearity of storage modes, even when the stabilization is off. So we can maintain performance even having stabilization off during all the CNOT gates, which is sort of a necessity because the CNOT gates would rotate you in a way that conflicts with the stabilization. And so there's a couple things we can look at. This one I'll go through relatively quickly, but when you do error correction, we expect, so we're like doing these joint parity measurements, and so you measure the joint parity once, then you measure it again, and you're just doing that repeatedly. That's sort of what the error correction constitutes. And what we expect is that unless some phase slip single photon loss event happens, which induces a phase slip, we should get the same result every like subsequent rounds. So for example, here we got the transmon was in G, but sometimes we'll see some inconsistency. And that's what we call a detection event. And that's meaning that either there was a measurement error or some like single photon loss event happened that we detected. And so this plot is just showing what is the rate at which we're getting these detections. And for 3 different photon numbers. So just look at the solid traces here, which are the average across each of the ancillas in the distance 5 device. And the noteworthy thing here, you don't have to be an expert on this, but let me just sort of assert to you that it's very unusual, and that, or not unusual, but it's very sort of nice how flat these detection probabilities are as a function of time, which is not at all a trivial thing. If you look at many experiments, these will grow with time. And that's not a problem in our system. We have, and it's usually like leakage on modes, which is propagating through the circuit and other things of this nature. In our system, these cat qubits are sort of like forming like a native leakage suppression. And so we don't have to worry about this at all. With like very little effort, we just get this extremely flat detection probabilities as a function of time, which is quite non-trivial. And so now we can look at a very key plot in the experiment. Here, we're plotting the logical phase slip error probability on the y-axis. So this is essentially, the smaller this number is, the better job we are doing of correcting physical phase slip errors with these joint parity measurements. And we're applying as a function of photon number on the x-axis. So this is, the photon number is the same for each one of the 5 cat qubits, or 3 if we're doing distance 3. And so the 3 colors here are, the purple is a distance 5 section, the blue is a distance 3 section, and the red is another distance 3 section. So we're comparing 2 distance 3 sections to a distance 5 section here. And what you'll see is, so just a couple sort of observations. As we increase photon number, the logical phase slip error probability increases. That makes sense. Where I have more physical phase slip errors, so it's more likely that some of these phase slip errors, once you have too many of them, it will start to confuse the error correction, and you'll have a higher probability of having a phase slip error. So that makes sense. Additionally, the distance 5 section outperforms the distance 3 sections across this whole range of photon numbers. The threshold photon number is probably around 4 or something like this. And that's not a trivial statement at all, because as we increase photon number, we know we're increasing the single photon loss rate of the phase slip error rate of each of the storage modes. So across this whole range of photon numbers, this repetition code is below threshold. And this is sort of a very nice feature. We're using this classical error correction, and so we can operate sort of well below threshold given the sort of simplicity of decoding the repetition code, which is one of the reasons this is very hardware efficient. And we can even fit these to like some functional form like this, where this number is sort of giving you like the effective, almost like the effective distance, or I guess effective distance over 2 of the code, or how many errors we can correct. And you can see that it's better for the distance 5 section as expected, or significantly better than the distance 3 sections. Cool. So that's the first thing. Now let's look at the complementary thing, which is the logical bit flip errors. So we just are discussing how we can, if we have phase slip errors, they'll be detected by these joint parity measurements, and then we were checking what the logical phase slip error rate is. The second thing we have to check, which is the harder part of the experiment, is what is the logical bit flip error rate? And this is the part of the experiment relying on the fact that how well are bit flip errors natively suppressed by the cat qubits, and sort of how well is that preserved even while performing the gates. Yeah, so we have this sort of repetition code, which is actively correcting phase slips, and all while we do that complicated circuit I was showing you before, we have to ensure that the bit flips remain suppressed. So we have this circuit, and the point here is just that when you're thinking about our logical bit flip probabilities, the thing to keep in mind is that any physical bit flip error on a cat qubit will lead to a logical bit flip error. So that's sort of why this is hard. Anywhere in the circuit we make a mistake, that will lead to a logical bit flip error. And so there's like crosstalk of many kinds, ancilla, measurement-induced state transitions, non-adiabatic resonances in the gate. All these things have to be extremely carefully dealt with in order to get this to work. And it has to be across all five cat qubits and all 8 C0 gates in the circuit for distance 5. And so how does it actually look? So now we're plotting the logical bit flip probability on the y-axis here. And on the x-axis, we have the mean photon number of the cat qubits. And so what we should expect is that as we increase the mean photon number, as I said before, the overlap between the coherent states is exponentially decreasing. And so we should expect that the bit flip probabilities on the individual cat qubits go down. So that's what you see at low photon numbers, is that the bit flip error probability on the individual cat qubits is being suppressed as we increase the phase space separation between the plus alpha and minus alpha coherent states. And that's being reflected in the logical bit flip error probability. Eventually, we reach some saturation for both distance 3 codes. And it's the same convention as before. So red and blue are distance 3, and purple is distance 5. So we still reach some saturation level at higher photon numbers. And this is due to second order processes in our ancilla. So like the ancilla decaying from, we have this protection from using this 3-level encoding. But if the ancilla decays twice during the course of the gate, then we can have a bit flip error. So that's what's causing this eventual saturation here. But these numbers are, and then another observation is that this distance 5 logical bit flip probability is roughly double that of the distance 3 codes. And that makes sense, because there's, as I said before, any physical error can cause a logical error on the cat qubits, any physical bit flip error. And there's just twice as many, roughly, locations on the distance 5 code. So that's why the error is roughly double for the distance 5 code. But we're quite happy with the performance here, because this is sort of the initial experiment. And if you look at the distance 5 section, at these sort of like photon numbers, say mean photon number of only 3, this includes errors from 5 cat qubits, 8 C0 gates, and is still under 1% per error correction cycle. So all 5 cat qubits are being stabilized, all that idling error is being added up, all 8 C0 gates are happening, readout and reset are happening, which could potentially induce errors on the cat qubits if we didn't have good tunable couplers. All these things are added together, and we still have under 1% logical bit flip error probabilities per cycle. Sweet. And so now we sort of have these 2 complementary parts. We have the sort of logical, what are logical phase flip probabilities? How well is this joint parity measurement working? And then we have the logical bit flip probability, which is how well, while we're performing this joint parity measurement, are we ensuring that bit flips remain suppressed? And so this is just reminding you from before. So the logical phase flip probability is this one that's increasing with photon number, because the single photon, the phase flip errors induced by single photon loss scale with photon number. And then logical bit flip probability is the one which is suppressed with photon number. So you can imagine that the overall logical error probability, which is the balance of these two, is optimized at some intermediate photon number. And so that's what we're showing here. So this is showing, again, these two distance 3 sections and the distance 5 section. In purple, the distance 5, and then in red and blue, the distance 3. And so you'll see that the distance 3 sections have optimal performance around, just around 1 photon, or like 1.25 photons, whereas the distance 5 section has optimal performance closer to like between 1.5 and 2 photons. And so what's happening here is that the distance 3 section has less protection against phase slip errors. So as soon as you start to go to a little bit higher photon number, the physical phase slip error probabilities increase, which causes the logical phase slip error probability to increase, and you just quickly lose out. On the distance 5 section, on the other hand, as we go to higher photon number, it's tolerable because the error correcting code can actually sort of handle more errors because it has higher distance. And so the optimal performance is a higher photon number. And this is, of course, heavily reliant on the fact that we have very good bit flip errors are being suppressed with photon number. If that wasn't the case, the distance 5 section would just strictly be worse. This is including the logical bit flip probabilities, and if you added those in without any sort of noise bias, they would just dominate all the error probability. Yeah, and a kind of nice thing here, this is a very early experiment, but these error probabilities are quite, I think, good for like these sort of error correction experiments, and this is just the sort of very first iteration. And there's not a formal threshold here because we're in sort of these, there's not a formal threshold here because we're in this, we're using a repetition code which only protects against one kind of error. The other error is corrected at the physical level. But I would call it like, I don't know, pseudo threshold or something like this, where we have comparable performance between the distance 3 and the distance 5 sections. Sweet. And another important thing I'd like to note is that the error budget in our system is dominated by the cat qubit bit flip and phase slip times. So in a sense, you would call this like a coherence limited experiment where we're just dominated by the intrinsic like the cat qubit bit flip times and cat qubit phase slip times, and specifically not the CNOT gates. The CNOT gates here, we've done a sufficiently good job that they're just not, the error budget is, they just essentially are a very minor contribution. Sweet, and I'll give you a quick outlook. So what I showed you is that we have this distance 5 repetition cat code, and we measure the logical bit flip and phase slip probabilities, and together we get this sort of overall logical error probability. And I would say this is a realization of hardware efficient quantum error correction using concatenated bosonic qubits. We're sort of using this like multi-level encoding where we are, instead of physical qubits, we have these bosonic qubits, which are encoding into a harmonic oscillator. And then on the outer level, we have this classical repetition code. So this is really realizing sort of scaling up bosonic qubits, which I think is likely going to be required to get sort of utility out of bosonic qubits. And secondly, this is, I think, one of the first examples of doing quantum error correction with noise biased qubits in gates. In this case, that's what allowed us to use this repetition code. So I want to talk about sort of the future directions here. And the key thing is that right now we weren't limited by these transmon-induced errors, but eventually, even with all the work we did with this like multi-level encoding, et cetera, you can always improve that by just improving like transmon coherence, for example, and improving gate in other ways. But you'll eventually be limited, even if you make like millisecond transmons, you'll eventually be limited. You're not going to get like 10 to minus 9 error because of these transmon errors. And so there's sort of, the future directions are how do we deal with this? The first way is you can use, and I won't go into too much detail because you can check out this paper, is you can use like a strip surface code. So I was showing the stream limit where you collapse from a surface code into a repetition code, but you can maybe just leave a little bit of the protection against bit flip errors. And then that will allow you to correct against, you'll be noise biased, but you won't be in the extreme limit where you have no bit flip errors. And so this extra dimension will give you some protection against those bit flip errors. The second direction to consider, and to sort of give context to this one, I'm showing one of our like cat qubits from the second paper. And this cat qubit is quite high performance. And so you'll notice that even at only 4 photons, we already have rough approaching second level bit flip times, I guess half second in this case. At only 4 photons, which is a highly quantum mechanical object. And so we'll come back to that in a second. But if we assume coherence limited performance consistent with these bit flip times, and so right now we have some saturation here, but we're very confident this will be fixed. Other groups, I don't know if they have shown like 100 seconds more bit flip time, so that will be solved. And I guess if you can realize those like very high bit flip times, but also with the like perfect scaling that we have here, then at already 8 photons, you would have 1,000-second bit flip times. And if we assume like millisecond storage T1s and say like a distance 15 repetition code, so it's only like 30 cat qubits. And sorry, just take a step back. And in the second direction, we're going to use fully noise biased Ancilla. So we have this transmon before, which was inducing errors on cat qubits. But we consider, for example, using cat qubits as our Ancillas here. And there's a key sort of catch here. But if you assume coherence limited performance, like this experiment, where we're just limited by how good are cat qubits, and you assume these parameters here, which are like, these bit flip times here are quite confident that will be reached. Nothing here is really a stretch, I would say. It's just sort of projecting what we have here and then improving T1s to what's been measured elsewhere. Then one can get logical bit flip and phase shift probabilities of like 10 to minus 8 with only 30 cat qubits, which I think is very exciting. That's like the first sort of utility application, like Fermi-Hubbard model simulation. I guess, I don't know if that's formal utility, but first sort of non-trivial things I think we know we can do with quantum computers. But the key ingredient here is a high-quality CNOT gate. And this means that this CNOT gate has to enable you to have coherence limit performance. It shouldn't introduce extra error. And so I think this is really the hard question here. But we think optimistic question, because as you've seen the sort of power of the superring circuit toolkit, that we can realize what we've shown here. And I just want to give some quick thoughts here, like 30 seconds maybe. This experiment I think is really, is well suited to this workshop because we're really showing the ability to print these extremely complex superring circuits. It's really taking advantage of the toolkit that's been developed over the last 20, 30 years. Additionally, I don't think you should be scared of distributive cat qubits. They can be really reliably made once you understand all the physics details, a lot of which are present in our papers and others. And lastly, it should be important to take advantage of noise bias in all aspects of computation. You can check out like this recent paper, for example, is just one of many examples of this. And always sort of an obvious comment, but keep an eye towards the scaling that we need to get to the long-term useful applications. So thank you, and yeah, thanks for the invitation to speak. And please check out these papers if you want more details, or come ask me any questions.
Great, thank you very much for this very nice presentation. I'm sure there's a lot of questions. Yeah, there's right away one here.
Does work? Yeah. For the very interesting talk, I was just wondering, maybe a basic question: how would you perform logical operations in this device? Or this
yeah. So there's multiple ways of doing it. Like anything that you would do, sort of like lattice surgery operations, you can do, for example, if you want between repetition codes. But there's also nice features, right? Because they're one-dimensional codes, the repetition codes. You can, not usually on 2D planar devices, but you can perform like transversal CNOT gates between repetition codes if you want to, because they're single one-dimensional. That wouldn't work for really anything beyond these one-dimensional codes. And then there's like this paper I was showing on the last slide. I mean, canonically, one would want to use like physical Toffoli gates perhaps to realize like a logical Toffoli. But there's this recent paper that I was linking on that last slide is from Diego, is showing some new ideas for doing magic state distillation, also taking advantage of noise bias to realize extremely efficient magic state distillation. So there's like a tremendous fruitful area of looking at ways of doing logical operations.
Okay, thank you.
Yeah, just pass it forward there.
Thank you very much. Very interesting talk. I'm trying to have some insights on the energy of these bosonic logical qubits. Is that determined by the mean photon number, or?
Yeah, or roughly speaking, these are just like 5 gigahertz modes, ish, and you see the mean photon numbers are still highly quantum states, so it's like mean photon number like 3 or something. So yeah, it's the highly quantum mechanical object still not much different than like a transmon, because we're only using like number of excitations you can count on your hand. Yeah.
Thank you.
Great. Any more questions from the audience? Yes, over there. Oh, this fell out again.
Thank you. Thank you for a very great talk. It was very nice to listen to. This is a really bad question, but I'm really intrigued. You do a repetition code in order to protect yourself against phase flips, wherein repetition code classically is a protection against bit flips. So if you redefine your block sphere, it would be the exact thing I do in classical repetition codes. Why did you decide that the block sphere had the encoding that it did?
Okay, calling us out. I think this is there are these 2 conventions in the literature. I don't know if Yvonne will use the other one in her talk, but you always have to be careful. I guess the reason we use this convention is that, think of it like what's an extreme limit of like a classical bit is like some light switch or something is an example often used. Then because it's the classical aspect, which in our case is a bit flips, is the aspect which should be very unlikely to happen because it's like the classical aspect. there's other reasons why what you said makes more sense, because if you're doing this mapping from the high photon limit to the Fock qubit limit, it makes more sense, the convention you're saying. So it's sort of just a choice. But maybe from the point of view that the bit flip should be the classical part, which is very unlikely. Yeah, but what you did, maybe, I hope I didn't confuse anyone with switching it like that halfway.
Go ahead.
Excellent. And then another point, a little more outlook. You say that we shouldn't be afraid of buffer modes. They are easy to work with when you get used to them. But to me, that's the most exotic element in your circuitry. So maybe can you put some pointers on how to fabricate these? That's a big question, but how can all of us in this room just start fabbing that from doing Josephson junctions?
Yeah, I think there's nothing extremely, like the fabrication, we use relatively, there's an inductor in the middle, which is a shallow junction array, but extremely shallow, so it doesn't require some crazy fabrication process. It's not like fluxonium where you have to be very careful about stray capacitances, et cetera. You can just, like, it's like, for example, a 3 or 5 qubit junction array. So all the fabrication is very standard. You just have to, this latter paper here goes into very much detail on, like, for example, unexpected sources of nonlinearities from like parasitic or like additional like serial inductances, which you can sort of take advantage of in a way to be useful. But these sort of essentially lead like inductances in series with your squid junctions. So there's a lot of details like this that are in this paper that should just be considered. But I think now that these details are understood, yeah, we really just not. I think hopefully in the next iteration there will be a lot of people talking about distributive cat qubits. Yeah, thank you.
Great. I think we can have 1 or 2 depending on the length of the questions. Yes, there's a question here.
Yeah, and hopefully nobody up top asks the question because I don't want to be responsible for throwing it up there.
Thank you. So do you think that the physical protection against bit flips in the long run is enough to stay with a classical error correction code?
Yeah, it's a very good question. Yeah, so I think this aspect of can the individual cat qubits get to like 10 to minus 8 or 10 to minus 9 bit flip error probably per error correction cycle? I think yes. That I maybe didn't think so myself 3 or 4 years ago, but now I think yes, that will be the case. So the cat qubits themselves will get to this limit where we have like 1,000-second bit flip times. That's sort of like sufficient for like the early sort of useful things one can do with quantum computers. The hard thing, as I was saying, is this CNOT gate. When we do the CNOT gate, can we do it in a way that not only does it preserve the bit flips, but also not induce a bunch of extra phase slip errors, which is maybe with the current gates, unless one goes to somewhat like daunting parameter regimes, might be the case. But the cat qubits themselves, I think yes. And then the question is, the catch, I guess, is doing the gates. But we think we're quite optimistic, I think, and there's because of the power of searing circuits to really make these quite complex Hamiltonians.
Great. With that, then let's thank Harry again. And then I would like to invite Christian Schönberger as the chair of the next session.
Thank you, Christian. So I'm also Christian. Christian Schönberger from the University of Basel and from the company Y Quantum. I'm going to chair this session on bosonic and hybrid qubits. And the first contribution is an invited talk from Ivan Gao from the National University of Singapore. And the title is Control and Measurements. We continue with Schrödinger cat states in bosonic circuit QED. Please, welcome.
Thank you very much for the introduction and the opportunity to share our work on this very big stage, and also to a lot of friends that are really experts in this field. So I think I'm in a very convenient time slot right after Harry, because he's already laid out quite a lot of the concepts for bosonic CQD or manipulations of bosonic qubits. So I thought I will switch up a little bit and talk about a certain aspect of bosonic CQD that perhaps we have been, overlooking a little bit. And that's about the measurement aspect. And I will go into why this is actually a little tricky and not as straightforward as what most of you may be familiar with in measuring a single transmon or fluxonium state. Okay. So a little bit about me and where our home base. So we're in Singapore, very sunny, urban place, very different from where we are. But something that's quite similar is that we do also have a quite diverse and vibrant quantum ecosystem. So we have a Center for Quantum Technologies, and this was established in 2007. So it has a long history with about 250 people, about 20 different research groups on a wide range of experimental and theoretical efforts. So I think together we've been working on all sorts of quantum information and quantum physics related topics over the past years. And my group is one of the fairly recent additions to the center. So this is us setting up the lab, our own fridges remotely in 2020 during COVID, because the Blue Force engineers couldn't come and visit us. After much struggles in the early year, first year or two, this is us, much happier, much more relaxed. Also have grown a little bit in size. So as a group, we've been quite busy over the past 4.5, 5 years or so. And primarily, we've been busy with playing with harmonic oscillators in the circuit QED context. Okay, so Harry mentioned that harmonic oscillators are excellent candidates for storing information and making logical qubits. So of course, that's one of the areas that brings a lot of attention, and it's something that we want to look into as well. But beyond that, I think, or at the same time, there are also other things that we think are really, really interesting that can be investigated using the bosonic CQED framework. So with the access to a harmonic oscillator in our device, we can look into things like testing quantum foundations, really exotic properties of just quantum interference and superposition, et cetera, in a very controlled way. We can also use them to demonstrate some proof of principle ideas in how to leverage non-Gaussian resource states in these quantum harmonic oscillators to provide quantum enhanced metrology as well as simulation. Okay, so we've been looking into all of these areas, and generally our typical device, our main playground, will look something like this. So I think we're all experts with the circuits. So you can see this is a very simple architecture, really, where we have two linear modes. So there's one oscillator, another oscillator, and in between we introduce a nonlinear mode. This is the simplest one with just a single junction, a transmon type of nonlinearity, but of course this can be changed into different, more exotic or dedicated special purpose nonlinearity as well. Physically, very often you may see 3D architectures for this because of the convenience as well as the possibility of getting really long-lived harmonic oscillators using these 3D cavities. So in the previous talk, I think you saw the planar version of something like this. And of course, the physics is exactly the same. It's just that with the 3D version, at the moment, we still have better coherence times, and as well as quite easy to set up, especially when you're, I guess, starting up and you don't want to put in all the hard work of getting the fabrication up and running seamlessly yet. So with this kind of very simple device, we can get a very good separation of the coherence timescales so that we can really have a testbed for light matter interaction. Okay, so we have our light, which is a stationary microwave field in this 3D cavity. So it just looks like a little cylindrical system with a stop in the middle, and then the rest of the area here are just vacuum. Okay, so that can go up to 1 to 2 milliseconds quite routinely with the transmon coupled to it. And our transmons are typically floating transmons living in this 3D waveguide or 3D tunnel, and that has typically coherence times of 100 or so microseconds. And next, the transmon, we often introduce just a very simple planar, either coplanar or strip line-like resonator to allow us to do quick readout of the transmon state. Okay? And here we typically couple this mode very strongly to the outside world so that we can extract the information fairly quickly. So this is a simple module. We have our long-lived bosonic mode. We have a controllable nonlinearity and relatively fast extraction of information. So that's great, right? And with this, we can do many things already, as simple as it looks. So over the past few years, actually, we mostly focus on exploring the following 3 areas. So the first one is about really looking at this from the physics perspective. So we're thinking about now we have a fully programmable light and matter testbed. So can we do some of the early ideas on quantum optics with our system? So there's actually a talk by my student Fernando, who's probably in the audience right now, that will talk about some of these ideas that we explored of how to tune these James-Cumming type of couplings and leverage them to study light-matter interaction in a more programmable way. We also looked into how to create and protect and use non-Gaussian resource states, such as CAT states, not just as logical qubits, but potentially as also resources for quantum metrology. So we have to work on this that got published recently. But today, I actually would like to focus on the last series of experiments that we just completed recently, which is to look into the measurement aspect. Okay, this talk will be mostly based on these 3 studies that we did, and some of the details all the details actually are here, as well as the code and algorithms we developed. They're all open source on GitHub. You can find the link on the paper, the published versions. Okay, so now let me go back to the device design a little bit, right? So I promised you a lot of good things about this device, and I said it's so useful and it's so convenient to construct. But something I haven't mentioned is that there is a small caveat about having this really long-lived cavity mode in our system. It's great that it's long-lived because we can interact with it for a long time. We can really, create very, very non-trivial states in it. But by design, it's also very weakly coupled to the outside world, which means that you can't really play the typical tricks of homodiene heterodyne detection in optics directly to extract the continuous field that's coming from the cavity. It's by design weakly coupled to the environment. So how we usually extract this information from the bosonic mode is actually by making the extra effort of mapping certain information of our preference onto a state of the transmon and then read out the transmon. Okay, so this is not super complicated if you look at it just like that, but actually with every step there is room for errors to creep in. But I guess it also creates opportunities for us to think about optimization. Okay, so this is a typical kind of workflow one would do just to extract quantum information from the bosonic mode. So imagine you have this harmonic oscillator. You can create whatever state you want in it, and now your end goal is to be able to get a density matrix. Right? Let's assume this is our final goal. Then to get there, very often we'll first have to figure out what kind of observable of this oscillator we want to map onto the ancillary mode. Right? So you heard from the earlier talk by Harry that they are mapping either parity or drawing parity on the transmon and then extracting the transmon state as the error detection scheme. Here it could be a generic kind of unitary operation that provides the mapping of a certain sets of observables. And then what we do to get the density matrix is to then exploit the whole phase space by displacing our continuous variables to various different points, so we accumulate enough independent measurements to do the reconstruction. Okay, so there are quite a few steps involved. The most typical example is the mapping of parity, which then gives access to the Wigner function, and then we can do a full tomography using that. So we have analytical sequence, such as this one, which is quite straightforward, but still, if you have a little bit of error on each of these steps, you will end up accumulating them once you start to do this with over many, many points in your phase space, right? But if we do this well, what we get is something like this, where you get a Wigner function. So you have each pixel is each displacement in phase space, and you accumulate the transmon state based on that to know whether it's G or E, which maps to even or odd at each point. And then using that, if you have enough points, then you can reconstruct the density matrix and figure out exactly what is in your cavity. Okay? So when we looked into this process, as we started our works in the past couple of years, we were thinking, well, this is pretty convenient, right? We use this all the time, but is there room for some optimization? Especially if you have existing hardware already, right? Let's say the optimization does not happen in terms of building new devices, but rather given an existing device, an existing set of conventional parameters, what can you do to squeeze the most out of it, get most information most efficiently and most accurately? Okay, so with that in mind, what we did is to look into each of the steps involved here and see if we can do some additional optimization to make it better. So the first thing we thought about is, of course, this key step that doesn't happen in the regular qubit measurement part, right? So we have to first do the mapping before we can do the qubit readout. Now, when we think about the bosonic state, this brings back to our perhaps quantum optics 101 kind of picture. We can think about several different phase-space representations, and that's the kind of thing that we have access to through this kind of mapping. So our starting point is to think about which one do we want to map. Right? We have some choices. I think the parity, which gives us Wigner function, is one of the most popular ones because of its utility for error correction. And also, it's nice to look at. It gives you the coherences right away. But are there others that we can choose from that's also natively available? Well, it turns out there are two others. Maybe not exhaustively, but two others that are relatively convenient to extract as well. One is the Q function, which essentially gives you information about the photon number, and as a result, you can reconstruct density matrix based on that. Okay? The other one is the characteristic function, which is a little more abstract, but essentially it boils down to the expectation value of the displacement operator. So we have developed as a community over time in bosonic CQUT to map these respective operator observables of the oscillator onto the qubit state through native gates on the transmon on the oscillator. So we have access to them, and they're also related. So one, essentially the Q function is a Gaussian convolution of the Wigner function, and then the characteristic function is essentially just a 2D Fourier transform. So in principle, if your measurements are perfect, all your operations are perfect, it does not matter at all which one you choose. You choose one, and you get a density matrix, and everything is done. You can move on. But in reality, very often there are many imperfections in the process. There are errors, both due to incoherent errors as well as coherent errors, just as what we heard in the past 1.5 days. So given that there will be imperfections, then what do we choose in order to maximize our chance to get the best reconstruction or density matrix? Is the question we wanted to ask. Okay, so. To maybe to put this more visually, one is the challenges we face is, first of all, this curse of dimensionality happens in the oscillator as well, because we have a large system, large Hilbert space with many photon numbers that we often use to encode a state. So we need to do many measurements in phase space in order to reconstruct that density matrix. The second thing is that when you do such a reconstruction, very often the errors get amplified through the inversion process, because now you're inverting a matrix to find out your density matrix. So this essentially calls for thinking or optimization about how can we minimize this amplification of errors. The next thing, which is kind of staring us in the face, is that we're also using another element, which is not a harmonic oscillator. It has a different error model, and is in fact most likely more prone to errors than the oscillator. Right? In our case, we have oscillators about millisecond lifetime, but the transmon oscillators are almost an order of magnitude shorter lived than that. So through this coupling, you get both coherent errors, which is the parasitic dynamics, because you have always on dispersive coupling, as well as decoherence due to ancilla, which Harry also talked about. Right? So with all these imperfections, what we want to do is to see which kind of observable is the best that can give us the most reliable information. So what we want to get out of should satisfy these requirements for it to be useful. It should be natively accessible, which means that we can just do analytical gates and do that mapping very easily. Ideally, it should be quite robust against decoherence and coherent errors. And finally, we want to be able to not measure so much, because with longer measurements, more accumulations or iterations, more drifts could happen in the system, right? So we want to measure essentially the minimum number of observables in phase space that allows faithful reconstruction. So with these goals in mind, we went back to thinking about all the observables we have access to, and we came up with something we call ORENS, which is an optimized reconstruction technique based on excitation number sampling, which is essentially just saying that we now want to reconstruct the density matrix, right, with minimum number of points, and then we map the excitation number onto the transmon, perform those measurements, and reconstruct. And this is actually exactly the same process as what's been studied many years ago. It's just generalized Q function. right? So we're not reinventing the wheel here, but rather we're looking at this in a slightly different light. This was actually used by some of my seniors at Yale quite a few years ago, but without any optimization on this, essentially accumulating as many points and just measuring the entire Q function, measuring the Q function with n equals to 0. So when we looked at this again, we realized there are actually some free parameters here that we can optimize that can maybe allow us to do better. So first of all, we can optimize where we go in phase space. We don't have to sample like on the grid throughout the entire phase space. We can sample more efficiently at well-chosen points. The next thing is which excitation number we choose could also be an interesting number to optimize, right? Because that should give us a way to think, depending on the size of the state, to really choose the mapping more efficiently, depending on the n. So this work, more details can be found here, but just to summarize, what we did is we first, of course, with our continuous variables, we have to impose a truncation dimension. We figure out where our continuous variable state lives. Then we optimize a set of displacements within that dimension, and we keep to the theoretically minimum number that's necessary to do the matrix inversion. And then finally, we optimized which photon number to map onto our transmon as well. Okay, so with this, we can actually implement it very easily on existing hardware. So that's another goal that I didn't articulate, but we wanted to be able to do this in a way that does not require extra hardware optimization. So with the standard device, what we did is essentially do this, regular displacement to sample different points in phase space. Then we do the mapping of a specific photon number operator through a selective pi pulse, which is a very long pi pulse that's spectrally selective. And then we read out the qubit. Okay? And what we see is that this is indeed much more robust, both to coherent and incoherent errors. So against coherent errors, there's some very nice intuition. So for instance, for mapping parity, which is the most common method in this, we're essentially suffering from this always-on parasitic dispersive shift. So our pulses are not exactly perfect. Of course, you can do some tricks to optimize it, to make it closer to being perfect, but this term is there, right? But when we map photon number, we actively use this dispersive shift because that gives us the spectral selectivity. Therefore, we don't suffer from parasitic terms. So this is quite convenient, and when we test this out, we actually see that in a slightly exaggerated way by tuning the pulse to be not so broad. We see that we can map photon number parity reasonably well when it's a small state, but as we increase the number of photon occupations in the cavity, it gets progressively worse. Whereas for excitation number mapping, we can do this consistently well. Now, the next thing we want to check is it robust against decoherence, right? So, the ancilla could decohere in a variety of different ways. Here we focus on the dephasing effect. Partially because our qubits were having bad T2s during that time in the lab. So conveniently, there's also some nice intuition, right? So compare again to Wigner function, which is the familiar default choice. When we map parity, we use pi/2 pulses, a Ramsey kind of effect, where we're on the equator the entire time before we refocus onto a qubit state. Whereas for photon number mapping, you just transit through the equator very quickly. Okay, so if you have dephasing, which smears out along the equator, the parity mapping is going to suffer much more compared to the photon number mapping sequence. So again, we did this just to do this mapping, not the full reconstruction yet. We see that as we artificially decrease our T2, we increase our dephasing effect, the photon number mapping remains reasonably robust, whereas the parity mapping suffers quite dramatically as you have more and more dephasing, which means you smear out more and more on the equator, therefore your Ramsey sequence doesn't work anymore. Okay, so now putting all of this together, we tested our full reconstruction by creating a test state, which is something like a kitten state in this case, and we perform a Wigner function at various different dephasing times, and we see that this is the ideal state we want to get. With regular Wigner, we actually have extremely distorted states. Okay, we can do double the amount of measurements to correct away the coherent errors. This is called the corrected Wigner, but which allows us to recover a little bit of the structure, but this costs us double the measurement time, and the resource, therefore the resource required is quite a bit higher. Now, if we do ORANS, we can use the theoretically minimum number of measurements and still capture all the key features reliably, even at relatively poor T2 times. Okay, so this is quite promising, and I think gives us, a very nice tool to really get more information out of the hardware, of existing hardware, if it suffers from, say, a large coherent error or significant dephasing for whatever reason. Right, so this is pretty handy, and we actually have experiments in the lab that are now actively using this tool on 2 modes, 2 bosonic modes, and that also gives us actually quite a bit of a speed up because we're sticking to the minimum number of measurements that's theoretically allowed. So now in the last few minutes, I will then go along this chain and talk about what else we could do along this workflow, right? So over here, I think many of you are experts already on measuring qubits, and this has been ongoing research for many years now. We constantly are optimizing the readout process for the transmon qubits or whatever qubits that we're dealing with. And for us, again, our motivation is not to then optimize the hardware further to improve the readout, but rather, given an existing readout hardware where your chi's and kappas are already set, can we then do something to just get more out of that, right? And for us, what we looked into is to optimize the waveform of the readout. So this paper actually talks about using the reinforcement learning process to come up with a more efficient pulse sequence, a pulse shape, to read out the qubit state after the mapping on existing hardware with typical devices. So without going through the details of this, essentially it's a model-free reinforcement learning agent where we give it a physically motivated cost function or reward function, and essentially it explores the multi-parameter optimization space on its own, and it finds whatever works best, right? So at first I was pretty skeptical. What if it spits out something that's completely non-interpretable? Do we gain something with that at all, right? What we saw is that, interestingly, all of the different devices we trained this on, so a wide range of chi over kappas for the qubit to readout resonator, we see that there's very good convergence of the optimization by the agent, and all the waveforms have a very, very standard and stable shape. Okay, so this little first kick, a continuous stable drive, and then a back kick that does the quick reset of the resonator back to 0, and then it finishes the process. Okay, and we're pretty excited about that. And actually, given I think this is even before my PhD time, maybe while I'm still a student. So this is actually a pulse called Clear that's developed by the IBM folks analytically quite a while ago. And it's pretty funny that actually the agent recovered essentially this, but a more smoothed out form and also a little bit more efficiently because you could optimize all the parameters at the same time. So what we did is in this study actually compare the agent's learned outcome with a Clear waveform as well as the default readout pulses. And we see that, well, they more or less achieve, the same best performance readout fidelity, but the RL version does it a little bit more quickly for the same device parameters. Okay, so just to show some standard histograms, the readout is good. We tested on our device as well as IBM devices across different chi and kappa ranges. So it really shows that whatever your optimized hardware is, being more filtering or dynamically changing chi, etc., maybe optimizing the waveform can still give you a little bit extra in getting your information quickly from the qubit. Okay, so let me wrap up by considering the final step of our workflow, which is essentially a post-processing step. We've mapped our observables on the qubit, we've read out the qubit state, now we have all these data points, right? These measurement outcomes. We need to do a reconstruction to figure out the density matrix. And this is conceptually pretty simple. It's just a matrix inversion process. But in practice, as I was mentioning, if you have any imperfections, this process itself can be very prone to amplifying those imperfections into something that essentially muddles the information that you will get. So what we did is to think about, well, given these imperfections, whether it's coherent or incoherent, can we do this in a way that maybe already accounts for some of it without doing in a naive map inversion? Okay, so what we did is essentially to use a learned process through a reservoir processing technique, and we essentially allow the mapping process to learn all the bad things that could happen, and then do the reconstruction more meaningfully. Right? Again, no optimization on the hardware, is whatever we already have, can we get more accurate information out of that, knowing that there are imperfections in the system. So with this, what we see is that is that when we create a kitten stage of different phases, so these are just even, odd, or superpositions of coherent state with a different relative phase, we see that if we use an idealized map, which is just where we'll calculate based on our model of the system, then we actually get quite a few spurious distributions in the density matrix, right? So if we just stop there and conclude that, oh, maybe our process is not so good, that could actually be misleading, because essentially our matrix inversion process is has amplified some of these that shouldn't be there. How we know that is that if we allow learning to take place, we use half the existing data to train, and then use the learn map to reconstruct the remaining half, what we see is that we can actually get, our state is actually much better than we thought it was. Right? And this is purely just because we're now doing the inversion in a much more educated way by actually allowing the map to learn from what's actually going on in the system. So this, again, is the final piece that allows us to really get back all the information, or as much of the information that we've lost through all these steps in measuring a bosonic state in our hardware. Okay, so putting everything back together, what we learned through this series of studies is that when we want to measure a bosonic state, we should think about which observable to choose. They are not, even though they are all connected, given imperfection in the system, choosing one over the other might have certain advantages. When we want to measure, we should also try, we should apply all the tools we have from the qubit measurement community that the community have developed and try to get the most out of that. And finally, when we do the reconstruction, we also just want to be careful of potentially, poorly constructed models. So you use learned dynamics instead of analytically constructed dynamics instead. Okay. So this is a series of study on measurement, as I mentioned, and then the rest of the works that I don't have time to talk about are in these papers, right? So maybe just to wrap up, those are the things we've already done in the past few years. So going forward, what we want to do actually is to continue to look at our bosonic CQD hardware as a little window towards light-matter interaction in this very controlled, highly nonlinear regime, right? So usually when we think about quantum optics, the photons, well, if you speak to a quantum optics person, they will say, oh, we don't have enough nonlinearity. And in circuit QED, that's something we actually conveniently have, and we have a lot of control over. So it's a very, very nice and powerful platform for us to test many of the existing quantum optics theoretical ideas. So in the team, we're currently exploring several of these things, for instance, creating mesoscopic superpositions in multiple bosonic modes to think about entanglement, what kind of entanglement witnesses and signatures one could observe when we start to push these into really large coherent state superpositions across many modes. We're thinking about how do we then untangle them, right? A little bit like the CNOW gate that Harry mentioned, but how can we do this differently such that we don't have to go through the intermediary ancilla, but rather really make it a pure bosonic interaction. So if you're interested in this, please feel free to write to me. And just to be cheeky here, since many of you are interested in very large systems, we always tell people that we're not scaling up, although scaling up is a very noble cause. But I think we're going to stick to what we know what to do, and what we're interested in for now is to look into small systems and use them as a test bed to build tools for the community that can contribute to scaling up bosonic systems, as well as to learn new interesting physics. And we're always hiring, I think, and we're very diverse team. I think generally we have quite a lot of fun and try to solve problems in the lab together with a sense of humor is very important. So yeah, if you want to find out more, please find me. I'll be here for all of tomorrow as well. And you can also check out our website or write to me directly. Thank you very much.
Thank you very much, Yvonne, for this wonderful talk. So I suppose there are questions. Are there questions? There's a question, where is the cube actually? It's just close by, so it's just next. Okay, very good.
Thanks for the great talk. I'm interested in your reinforcement learning readout process. So one question I have is, do you constrain the maximum sort of drive strength or the photon number that goes into the resonator, and do you consider measurement-induced leakage in your cost function?
Yeah, that's a great question that I didn't have time to go into. So what we did is, indeed, we put these constraints, but we put it in a way that is, we put it in a calibrated way. So what we do is we take the best readout. So some of these experiments are done on the IBM cloud devices. So we take their best readout, we calibrate all the relevant parameters from there, and we say that we don't want to exceed these numbers. Can our agent, given these same constraints of their best readout, do better? And so for each of the device, the exact constraints are slightly different because we calibrate their existing best readout. But yes, we do always constrain the maximum photon number, as well as we compute the leakages and decays as well, benchmarked against the default best performing readout.
Thank you.
Yeah. Yeah, there's a question in front, so maybe. Wow, that was a big shot.
Thank you very much. Very interesting talk. In one of your first slides, you highlighted that these harmonic oscillators have a challenge in the sense of that they are very sensible to interacting with the environment.
Okay.
Is that correlated to the thermal noise, or how do you cope with this?
You're talking about the interaction with the nonlinearity?
With the environment, you highlighted.
With the environment. Yes, okay. Yes.
On the first slide, sorry. Maybe
that's
you don't
right,
need to
that's
go.
right, yes. Thank you.
Exactly,
here, right, yes. So indeed, we intentionally make sure they are very isolated from the environment because we want them to be as high Q as possible. So the internal Qs of these guys are extremely high. They're 10 million or something like that. They can be very high.
And you are on a cryostat then?
Yes, at 10 millikelvin. Yes. And then when they have high internal Q, we don't want the coupling Q to limit them, so we make the coupling Q even higher, so they're very, very weakly coupled.
Okay, thank you.
Further questions? Okay, that's far distance, so for the cube to fly to. So let's see.
Hi, thanks for a great talk. Maybe it's a bit naive question. So the dimension of the state you want to reconstruct from cavity and then mapping into qubit. So what does it depend on? Is it like one qubit is enough for that? You just need to do many measurements? Or is it like you need to increase qubit, which could help also?
Yeah, no, that's a really good question. So in bosonic CQD, in these architectures, essentially, for a single qubit, let's say if you want to reconstruct a state, you do the X, Y, Z, the different polys, for instance, or whatever the basis you want, and then you reconstruct from there. So how we get that in a continuous variable version is by displacing to different points in phase space. So if you remember all these nice Wigner functions Harry showed in the earlier talk, each pixel is a different measurement of the qubit after mapping the parity at that point in phase space onto the qubit, right? So this is the one that the number of displacement in phase space is the one I was talking about, which we want to keep to the minimum possible. Yep.
Maybe a final question? No, there's one there in the middle, or maybe fifth row there. Yeah, good.
Thank you for a great talk. Maybe I skipped it, or maybe I just don't know enough about bosonic transbond couplings. I would like to. You told us that you could optimize over which Fock state you were trying to couple to, and you said you can just do that by a simple drive on the transbond. Can you just elaborate how that interaction looks like and how you can fine-tune which Fock state you're coupling to?
So I think there is a small, either I misspoke or there is a slight misunderstanding. This is not about coupling to it, it's about mapping. So the coupling is the standard dispersive coupling between the transmon and the bosonic mode. So it's always this dispersive shift, which is a state-dependent frequency shift. So when I say which Fock state to map to is just a simple pulse, is essentially using this spectral separation so if you think about it from the transmon's perspective, because of the dispersive shift, different photon numbers in the cavity is going to shift the transmon frequency to different points spectrally. And if I make a selective pi pulse, by driving those specific frequencies and make it narrow enough spectrally, so long enough in temporal dimension, then I'm selectively addressing only that photon number. I'm mapping that onto the transmon. So this pulse is essentially saying, flip the qubit if I'm in this N. And the only requirement here, so this is all programmable on the fly without changing the hardware, is just you need to be spectrally selective enough compared to your Chi.
Thank you very much.
You're welcome.
All right, so let's thank the speaker once more. Yvonne, thank you very much.
Thank you very much.
Okay, microphone still works. That's great. Okay, next speaker is Sergei Hazanov from Weizmann Institute of Science. Title is Enhancing the Cat Qubit with Autoparametric Dissipation. Please.
Hello, everyone. My name is Sergei. I'm from the Quantum Circuit group at the Weizmann Institute. And we just heard two wonderful talks involving cat qubits. Today I'm going to tell you about a different kind of cat qubit known as the cat qubit and how we can improve it. Now, before we dive into that, I will start by repeating some of the motivation for us studying this kind of qubits. So, error correction, quantum error correction is hard. The very nature of quantum information means that there are two kinds of errors we need to deal with, the bit flip and the phase flip. This means that our quantum error correction schemes are going to be hardware demanding. For example, the popular surface code involves encoding a single logical qubit on a 2D grid of physical qubits. This means we are going to have a bunch of physical qubits to correct for the bit flips and another bunch of physical qubits to correct for the phase flips. Now, what if we had a qubit which has only one type of error? We call it a bias noise qubit. So, for example, a qubit which has only phase flips and no bit flips. So, as we saw before, in this case, quantum error correction becomes a bit easier, and we can encode a single logical qubit in a 1D repetition code, and we have to only correct for the remaining error. Now, as we saw before, the kind of code that allows us to have this bias noise qubit is, for example, the two-legged cat code, where our logical 0 and 1 are going to be two opposite phase coherent states, alpha and minus alpha, or right and left coherent states. And their superposition, the even and odd cat states, are going to be the plus and minus states. As we saw, the advantage in this encoding is that we can suppress the bit flip rate exponentially, but by increasing the size of our coherent states, basically taking them further apart in the phase space. Now, there are no free meals, of course, and the larger our coherent states, the more single photon loss we are going to have, which means that our phase flips are going to be more frequent. Luckily for us, this only increases linearly with the size of our coherent states. Okay, so before we saw a kind of stabilization scheme known as dissipative cats. Now we are going to see a Hamiltonian kind of stabilization scheme. So for the Kerr cat, we are going to need only two components. We're going to need kernel linearity, whose magnitude is denoted by K, and two-photon drive or squeezing with magnitude P. And I really want you to remember these two quantities, K and P, because we're going to need it for the rest of the talk. Now, to understand how this Hamiltonian stabilizes a two-legged cat, we can either look at the Hamiltonian, which is it's very easy to see, but we can gain some intuition from the following description. In this Hamiltonian, we are essentially trying to pump energy into our oscillator, but the more energy we are putting into the oscillator, the less effective our pump becomes, because the kernel nonlinearity shifts the frequency, resonance frequency of our oscillator. And at some point, we will be putting so much energy into the oscillator that it's no longer effective, and we end up with two coherent states. These two coherent states are going to be the degenerate eigenstates of our Hamiltonian, and we can actually draw a metapotential for this Hamiltonian, and you see that it's going to be a double well potential. Our two knobs, the K and the P, or the ratio P over K, is going to determine the distance between these two wells and also the height of this barrier. So the larger this ratio, the larger our coherent states, the further apart these two wells and the higher the barrier is. Okay, so is this a much easier way of implementing the two-legged cat code? And is it perfect? Well, unfortunately, the answer is no. Unlike the dissipative ket, we see that as we increase the size of our coherent states, as we increase the ratio of P over K, we are not seeing an exponential increase in the bit flip time, but rather we see this staircase pattern. Now, it took the community some time to understand why this happens, but it turns out that the culprit are the excited states of this Hamiltonian. And essentially, any leakage or heating event taking us from the bottom of these two wells, from the computational subspace, taking us up, will result in occupation of the excited states, and therefore also to additional tunneling mechanism between the two wells, which translate to bit flips. Now, for the rest of the talk, I will discuss how we can suppress this leakage-induced bit flips. So let's continue. We have three different solutions for dealing with this leakage-induced bit flips. The first one is very easy to implement. It is the tuning, the squeezing. We'll see in a moment how this works, but this is effective and easy to implement. And the two next solutions will involve cooling down the Kirket qubit to the ground state manifold. We can do it with single photon dissipation and two photon dissipation. We've done both, but I will focus on the two photon dissipation, which is the ideal solution here. Okay, so let's start by looking at our experimental setup. Our Kirket qubit lives in a two-snail dipole. This is a very typical setup, but our readout resonator, which also will serve as a buffer, as we see, is actually flux tunable. And this is implemented by embedding a pair of squids into our 1D resonator. And these two modes are the flux is controlled with two magnetic flux hoses. Here is the image of how it looks in 3D, and on the left you see our chip. So let's start with the first kind of solution, which is detuning the Kirket qubit. To understand why detuning our squeezing is actually beneficial here, we need to go back to the intuition I tried to convey previously, and that is that if we pre-detune our squeezing, if we set it to not exactly the right frequency of the oscillator, but to some detuned frequency, we can actually pump more energy into the oscillator before the Kerr makes it ineffective. So essentially, this detuning the delta counters the effect of the Kerr. Now, and the result here is that for a given pump amplitude, we're going to get a bigger ket states or coherent states. The second and even more interesting result is that when we set the detuning to be some integer n times twice the Kerr nonlinearity, we actually force the first n pairs of excited states to be degenerate, which means that they're not going to contribute to the tunneling. And this is what you see. This is what you see in the simulation here at the bottom right. Okay, so let's see how it looks in experiment. We can essentially have a phase space diagram for these three parameters: the pump amplitude and the detuning over the Kerr. And we see here that we have three regions of stability, but we are interested only in the region where we are stabilizing two coherent states. This is the blue region. And if we stick to this region and try to maximize the detuning, we will see a very nice scaling in the lifetime. So, for example, if we start here at a relatively low pump amplitude, we get a modest 56 microsecond lifetime. But as we increase and make sure that we stick to the edge of the blue region, we'll actually go to an order of magnitude higher, almost 700 microseconds. We can continue to 2 milliseconds, which is already state of the art in terms of Kirket qubits. And we can probably push it a bit more. I just didn't have time to calibrate this figure. Okay, so now let's move on to our second solution, and that's really the kind of ideal solution we can do, and that's introducing a cooling mechanism which will keep us at the ground state manifold. To do so, we will now use our flux tunable buffer, which we saw previously, here on the right. And the kind of interaction we are trying to implement is a 2-to-1 exchange interaction between our Kirket qubit and our snail. combine it with a strong single photon dissipation on the buffer will mean that we have a one-way street for pairs of photon to be dissipated from the Kerket qubit. So two pairs of photon will go to the buffer and then decay rapidly through the buffer. Now, once we have this kind of interaction, we can actually aim it at the excited state of the Kerket qubit by slightly detuning this frequency matching condition, which we reach by tuning the buffer to this frequency. And this way we implement a way to depopulate the excited states of the Kerket qubit. Now, the real advantage with this method is that this two-photon dissipation can be as strong as we want, because two-photon dissipation does not affect the computational subspace. Losing pairs of photon does not affect neither the coherent state nor the ket states. And we actually managed to implement this interaction. Here on the bottom right, you see the signature for that, where we actually map the two opposite phase coherent states in the Kerket qubit to the same state in the buffer. So this means that it's really the signature of this interaction. Further down the line, we want to show that this indeed improves the lifetime, and what we can do is envision a new scheme for the Kerket qubit, which we call the auto Kerket qubit. Whenever we want to freeze the state of the ket, we want it to live for long time, then we set the frequency matching condition to be such that the buffer is twice the Kerket qubit, in which point we have two-photon dissipation. And if we want to do a readout or some other gate, we change the flux of our buffer, and we can perform operations. In fact, there is a third interesting point in this diagram, which is the point where the Kerket qubit is 1/3 of the buffer frequency. In this point, we can do a more efficient quadrature readout. I will not discuss this point here, but you can come ask me later. With this, I would like to finish and thank my collaborator, especially Misha here on the left, who did all the fabrication and the design of the flux hoses. I'll be happy to take questions.
Thank you, Sergey. Thank you very much for this wonderful talk. Question, please. It's hard to... Over there? Ah, there. I see that maybe 7th or 8th row on the left side.
Yeah, I was wondering if you guys have thought about, like with the single photon loss, inducing phase flips.
So
have
can you just repeat?
With regard to the single photon loss inducing phase flips, have you looked at using like colored dissipation?
Yeah, exactly.
Because then you can get much higher. Like once you do that, then I don't think is really much concern about the single photon loss, because you're gonna. Yeah.
Thank you for the question. It gives me the opportunity to show our results with that. So indeed, we implemented this kind of dissipation where we just do the single photon dissipation by applying a pump tone and aiming this interaction at the excited state. Indeed, we see increase in the lifetime. Here, in this case, it's an order of magnitude. We go from 200 microseconds to 2 milliseconds. And I would say there are two issues with this approach. The first one is that we have to pump this interaction, which means that we are going to end up with some heating effects. This is why this is the reason why we stop here. And second is that it's fundamentally limited. So even if we are colored, even if we are centered around the excited state, we cannot increase it indefinitely. At some point, the strength of the interaction will start affecting the computational subspace.
Yeah, I think I agree. It's just that gap is like 4K alpha squared. So if the curve is like scale of megahertz, then that limitation is way beyond what one could achieve with two-photon, or so far what has been achieved with even the more aggressive two-photon dissipation. But I take your point.
Yes, so I would say that just that for the Kerket qubit, you really don't need that much two-photon dissipation as you need for the dissipative ket. In dissipative kets, the figure of merit is the ratio between two-photon loss and a single photon loss. And here, the two-photon loss we are aiming for with our scheme is only 20% of the kernel linearity, which is already very small.
Okay, is there a further question? Short question or no question? I don't see any. So let's thank Sergey again. Thank you very much. So we go on to a talk on hybrid qubits, given by Jane Hai Soon from the University of Copenhagen. The title is Uncovering Intrinsic Loss Mechanism in Super Semi-Nanowire Gate Mounts. Please.
Okay, good afternoon. Thanks for giving me the opportunity to present our work. Today, my presentation will be uncovering intrinsic loss mechanisms in super semi-nanowire gate mounts. I'm a Chen Hai Sun. I'm a postdoc in SQA lab from University of Copenhagen. I would like to start my presentation with this figure. In this figure, it shows the family of superconducting qubits. In the next about 12 minutes, I would like to bring your attention to this type of qubit, which is a gate mount. This type of qubit offers the opportunity to have full electrostatic control of your qubit. We can also build a more exotic circuit with this type of qubit. For example, we can have Andrew spin qubit. We can also have parity protected qubit. We can also use this type of qubit as a platform to use a CQD technique to measure or to study the fundamental condensed matter physics. Before diving into our work, I would like to give a short introduction about what a gate mount qubit is. The main difference between a transmon and a gate mount is the difference between the junctions. In the left, I'm showing you the junction which is the beating heart of the conventional transmon qubit, which is the SIS Josephson junction. It has the superconductor, insulator, superconductor sandwich structure. It gives this sinusoidal energy phase relation. There's another type of junction, which is SNS Josephson junction. It has this superconductor normal metal superconductor sandwich structure, and the electrons, the holes in the normal region, can go through a series of Andrew reflections and can form Andrew bound states. The supercurrent can be carried from one side to the other side by these Andrew bound states. Now, if we use a semiconductor in the normal region and put a gate next to it, we can have a gate-tunable Josephson junction. And the energy phase relation is non-sinusoidal anymore. Here, tau is the transmission coefficient of the corresponding Andrew bound state. Now let's see what will happen if we put these two types of qubits in the superconducting circuit. In the left is the circuit of a flux-tunable transmon. Here we use two SIS junctions and put them in a square loop. By tuning the external flux, we can change the interference between the two SIS Josephson junctions. In this way, we can have this periodic qubit frequency tunability, as you can see in the bottom left. In the right is a gate mount circuit. Here, instead of using two SIS Josephson junctions, we can use only one single SS Josephson junction and have a gate line next to it. Because we are not tuning the interference between the two SS Josephson junctions, we are tuning the mesoscopic property of the junction itself directly. We will not have this periodicity anymore. Instead, the qubit frequency tunability will look like this, which is shown in the bottom right. For the people who are not familiar with the gate mount, I would like to show you how a gate mount qubit looks like in real life. If you zoom out a little bit, you will see the gate mount qubit actually inherits the design of a transmon qubit. Here is an example of an X-shaped qubit capacitor design. And if you zoom into the junction region, instead of seeing an SIS Josephson junction, you will see, in this case, a nanowire. And if you zoom in more, you will see the nanowire has this semiconductor core and has a superconductor shell. This superconductor shell can introduce superconductivity to this semiconductor. And here, we etch a segment of a superconductor to form this SNS Josephson junction. Since 2015, the first gate mount qubit is realized. People have put tremendous effort into realizing the gate mounts in different materials and different platforms. For example, the nanowires, also 2DECs, also in carbon nanotube and graphene. With all this effort, now we are at 2025. Sorry for the low resolution. The gate mount T1 is still at a 10th microsecond level. And in this conference, in comparison, we are already talking about millisecond level transmon T1 time. It seems like the gate mount T1 is hitting some ceiling. And it raises up the question that is there any loss mechanisms that we don't understand in gate mounts, which limits the Gitmo T1. This is where our work comes in. The first step we did is this T1 budget analysis. Here, we want to analyze the contribution from different loss mechanisms. In the left is an SEM of our device. You can see the qubit and the readout resonator. And in the right is a representative T1 data of Gitmo at different qubit frequencies. And the first loss mechanism we considered is Purcell effect. Because we need to couple the qubit to the readout resonator, this introduces the loss channel to the qubit. From what you can see from the right plot, the theoretical limit of the Purcell effect is much higher than the qubit data. So we are not limited by this Purcell effect at all. The second loss channel we considered is the spontaneous emission, because for this Gitmo to work, we need to bring the gate line close to the junction in order to have this gate tunability. If we don't carefully design the qubit gate line, the strong capacitive coupling between the gate and the qubit can introduce huge loss to the qubit. Now we have already carefully optimized the design of the gate line. In this case, in the 3 to 5 GHz regime range, the T1 limit from the spontaneous emission is much higher than 20 microseconds. So our Gitmo T1 is not limited by the spontaneous emission anymore. The third loss channel we consider is the internal loss. However, you cannot measure the qubit internal loss directly. Now here I'm using the Bayesian internal quality factor as a proxy. So in the right, what I'm plotting is the lower bound, because the qubit has a different geometry compared to the resonator. That's why, in general, the qubit should have higher internal quality factor than the Bayesian resonator. So here, what I'm plotting is the lower bound of the T1 limit because of this internal loss. As you can see, even with this lower bound, our Gitmo T1 is still lower than the theoretical limit. We can also combine these 3 loss channels together. Here, in this case, even with these 3 loss channels, our T1 data is twice lower than theoretical limit. This inspires us to think about there is some intrinsic loss mechanisms in the Josephson junction itself. So we designed this experiment. In this experiment, we have 3 types of qubit. They all share the same qubit capacitor design. And the first type is a transmon, where all the couplings are optimized. And the third type is a transmon, but with a Gitmo design. By that I mean we replace the SI nanowire with the metallic SI junction and keep all the other elements the same. And the third type is the Gitmo. By measuring the first type of qubit, we can have a baseline of how good we can make a qubit based on our current fabrication recipe and material. And by comparing the transmon with the Gitmo design and the Gitmo, we can isolate the intrinsic loss mechanisms. So we fabricated these 3 types of devices, and here are the SEMs. We measured the qubit T1 of these 3 types of devices. For the transmons, we can get over 100 microsecond T1. And with the transmon with the Gitmo design, we can get around 70 or 60 microsecond T1. And for the Gitmos, the best T1 we can get is around 10 microseconds. We can also analyze this data in a different way. Here in this plot, the 2 green data points are the T1 from the transmon with the Gitmo design. This T1 should already include the loss from the material and from the design. And then we extrapolate this T1 to different qubit frequencies. As you can see, our Gitmo T1 is much lower than the theoretical limit. So this is a strong indication that there is some intrinsic loss mechanism in the SS junction itself. And of course, this is not the only device we have measured. We have put a lot of effort. We tried to measure the Gitmo with the aluminum as a control layer. We also tried to use titanium nitride as a control layer. Among these 2 types of materials, our Gitmo has similar performance. But unfortunately, they are below the theoretical limit. There's actually another loss channel that we haven't included in our loss analysis, which is quasi-particle poisoning. This is well studied in the transmon community. In general, it can be revealed by this T1 as a function of temperature measurement. In the bottom left, I'm showing you 2 data sets from our devices. By fitting these 2 data sets with this formula, we can get the initial quasi-particle density and also the superconducting gap. In this case, as you can see, the T1 drops dramatically at around 150 millikelvin. For the gate amount instead, I need to remind you that the superconducting gap there is induced superconducting gap, which means the induced superconducting gap is not necessarily the same as the bulk superconducting gap. It can be smaller. Also, studies have shown that there can be non-zero in-gap conductance. These two factors may have increased quasi-particle poisoning effect on the gate amounts. However, we don't have time to finish the measurement before this conference, but if our hypothesis is true, we suspect that the gate amount T1 will decrease at a much lower temperature than 150 millikelvin. And also because of this high quasi-particle density, the T1 is lower, initial T1 is also lower than the transmons. With that, I would like to thank my team, especially David Bafil, Shekhar Singh, and Kasper Wei, and thanks for your attention.
Thank you very much for this very interesting observation talk.
Thank you.
Are there questions? Yeah, there's one. The cube is now here, so yeah, no, I can throw. Let's see, I can do this. Okay.
Okay. Yeah, thanks for the presentation. I was wondering, so if I understood correctly, it's the semiconducting core that you think might be attributing a lot to the loss. So what if you could make only the junction out of a semiconductor and not have a semiconductor core throughout the rest of the superconductor?
Yes, very interesting and also a tough question. Ideally, yes, the SS junction I'm showing here is not a pure NS Josephson junction.
Yeah.
However, I think from material science point of view, it's easy to grow semiconductor on top of a superconductor on top of a semiconductor, but it's not easy to do the opposite way. So you can have superconductor shell, then if you grow semiconductor on this superconductor, it cannot be grown epitextually. That's the reason why we don't have the pure NS now.
Yeah, are you aware of any examples where they tried to do this and they got a good or a bad result, or where they have tried to just have a thin semiconductor as the JJ, basically?
I'm not aware for now.
Okay, me neither, so I was just curious. Yeah. Okay, thanks.
There's a question now, that's really far distance, so somehow it has to hop. The cube should hop from, to the other side. Yes.
Yeah, so you said the loss mechanism that you think is because of quasi-particle poisoning. So is that poisoning of the Andreev bound states in the junction that you're saying is the loss mechanism here?
Not really. Okay. So here, for example, in the right plot, you can see the red line is they use evaporated aluminum. That's why you have this in-gap conductance. So maybe in our nanowires, they claim these are hard. There is hard gap, but the nanowires are different from each other. So maybe the ones we have measured has some non-zero in-gap conductance. That may cause this quasi-particle poisoning.
So you're not applying magnetic field, right? So
no, we don't.
Should be quite hard.
But even it's quite hard at a zero bias, there should be that can be non-zero conductance.
Okay, thanks. Yeah, I thought because if it was in the junction, then maybe try a quantum dot. But I guess if it's just in the superconductor already, then it doesn't help. No.
Yeah.
Yeah. All right.
Did you change somehow the length of the normal part to compare different junctions with different lengths?
I think for us, it's hard to control the edge. So we cannot make it 50, exact 50, 100, 150. For now, it's like 200, around 200 nanometer junction.
And that's already in between short to long junction limit, I suppose, right?
Yeah.
Okay, good. Any other question? No? Thank you very much. Oh, there is one. There was one. There was a question up there. Let's just come down. Yes.
Hello. Thank you for the great talk. I just had a question. So not in terms of the lifetimes, but about the gate bond itself. Did you try backgating the gate bond and maybe have an idea of the rough gate voltage that you should be applying to modulate it for the purposes that you're looking after?
You mean the plunger? What gate do you?
Or I guess I'm just wondering what order of magnitude gate voltages are you actually applying to the gate mod?
That highly depends the leverage arm. It can change from millivolts to volts. Yeah.
Thank you.
Yeah.
Okay, so thank you once again. All right, we come to the last talk of this session. It's given by Tobias Bonsen from TU Delft. And it's about spin circuit QED in the time domain.
Yes. Thank you. Yeah, thank you very much for the introduction, and I'm very happy to be here. Thanks also to the organizers. I'm having a great time at the Superconducting Qubits and Algorithms conference. But I would like to start my talk with a small confession. I do not work on superconducting qubits or algorithms, but instead on semiconductor spin qubits. So why am I here? Well, it's because in our project we try to couple these semiconductor spin qubits to superconducting resonators in what we have started calling spin circuit QED. So why do we want to do this? Well, this is of course a scary statement to make here, but semiconductor spin qubits are a promising candidate for quantum computation. Because of their good coherence, they could also benefit from the advanced semiconductor industry, and they could be integrated into very dense spin qubit arrays. However, the small size of these qubits also makes scaling to large qubit numbers challenging. And this is mainly due to challenges in the gate fan-out, and then also the need for these charge sensors on the side of the array. So we think that, hopefully it works, yeah. So to tackle these challenges, we think we might be able to take some inspiration from circuit QED with superconducting qubits, which has enabled the creation of devices such as this one, which is a 7-qubit processor accessible via the Quantum Inspire platform here in Delft. And the scaling of these kinds of devices really seem to have benefited from like 2 key capabilities of circuit QED, namely these long-range qubit couplers and the ability to perform dispersive readout using readout resonators. So combining these two, a large-scale spin qubit processor could look something like this, where we have interconnected spin qubit registers together with on-chip classical electronics to perform tasks like multiplexing. And taking inspiration from circuit QED, these quantum links between registers could then be implemented or realized using a superconducting resonator. And potentially, we could also use resonators to perform dispersive readouts via the quantum dot gates. And this would not need these extra charge sensors. And what I talk about today is our efforts over the past few years to realize, the first one. So a resonator-based quantum link between distant spin qubits. So how do we go about this? Well, we start from our spin qubit, which is formed by trapping single electrons in a thin silicon quantum well, and then applying magnetic fields to split the spin levels. And then we connect, and for that we use these metal gates on top to shape the electrostatic potential, forming these quantum dots. And we then connect one of these metal gates to an on-chip superconducting resonator. But the direct coupling between the resonator field and our spin, or the magnetic moment of our spin, is quite weak. So therefore, we take an indirect approach, and we first couple the resonator electric field to our charge qubit, which is formed by delocalizing the electron wave function over a double quantum dot. And then we place micromagnets on top of the device that generate a magnetic field gradient, and that leads to a hybridization of these spin and charge states. Together, this gives us an effective spin-photon coupling of roughly 20 megahertz, depending on the exact tuning of our device. And then looking at our resonator, it looks a little different compared to your typical circuit QED resonator. So it's made from a thin niobium tinitride film of roughly 6 nanometers. and this leads to a high kinetic inductance. This has two advantages for us. Well, one, this allows us to use a resonator with a very small cross-section, making it more resilient to the magnetic fields we need for our spin qubits. And it also leads to quite a high characteristic impedance. And this enhances this coupling between the resonator and the charge, and therefore also in the end our spin photon coupling. Now, I'd just like to mention that the device that we use in this work was fabricated by Patrick Harvey-Collard, was then a postdoc in our group, and now has moved to IBM in Zurich. Okay, so when we operate this device, we are always dealing with these 3 degrees of freedom. We have the photons in our resonator, and then the charge and spin degrees of freedom in the double quantum dots on both sides of the resonator. And when we cool down this device, we always start by just looking at the resonator or our photons. By just performing a resonator spectroscopy, we then look something like this. And when we then probe the resonator on resonance and start applying DC voltages to our quantum dot gates and varying those, we would get something like this, where for the most part, the charge configuration in our quantum dots is stationary and the resonator is unaffected. But for some combinations of gate voltages, the charges can move within the quantum dot area, and this leads to a downshift in the resonator frequency. And this then allows us to map out the charge occupation as a function of these gate voltages. And for our experiments, we then focus on this interdot transition, where there's just one electron in our double quantum dots. And here at the center of this interdot transition, the electron wave function becomes delocalized over this double quantum dot, and that's where the spin-photon interaction is turned on. And at this point, we can then start characterizing our spin and charge frequencies. We do so using standard two-tone spectroscopy. So again, probing the resonator on resonance, while now also sending an additional microwave tone to one of the quantum dot gates. And we can then tune the frequency of both our charged qubits by varying the interdot tunnel coupling between the dots, and also our spin qubit frequency by just varying the applied magnetic field. For the first set of experiments, we then focused or tuned the system to the dispersive regime, where the charge qubits are placed above both the spin and the photon, and the spins are both placed slightly below. And this regime is well suited to realize an I-swap gate between these spins that's mediated by virtual photons in the resonator. This is also what my colleagues Jürgen Dijkema and Xiao Xue set out to do. And they did so by tuning in and out of this point where the spin-photon interaction is on both sides. So I'll walk you through the sequence. So first, they initialized both spins to the ground state by just using relaxation. They then prepared one of the spins to the excited state using microwave burst. They then turned on the direction simultaneously on both sides for a certain time. And finally, also used the resonator to perform a dispersive readout of both the spins sequentially. So in using this, they were able to observe these oscillations, which was great because this was really the first demonstration of a resonator-mediated two-qubit operation in this architecture. So here on the y-axis is the integrated signal, which is proportional to the spin-up probability of each of them. And on the left, we prepared qubit 1 to the excited state, and on the right, we prepared qubit 2. And then two key observations to be made here is that the readout visibility for both our qubits is a bit different. And then also the oscillations decay towards the ground state, which is caused by the significant relaxation we have when at this operating point where the spin-photon interaction is on. The spin-spin detuning could then be varied using the fact that the micromagnets on both sides were placed at a 15-degree tilt. And this then allowed us to tune the spins in and out of resonance by varying the orientation of our applied magnetic field. And in this way, we could measure also these chevron patterns. And then finally, also in this regime, we increased the spin-photon coupling by bringing the charge qubit on both sides a bit closer, and then also detuning the spins a bit further from the resonator. And this then led to these accelerated I-swap oscillations, which also shows the tunability of this interaction. All right. Then in a new set of experiments, we moved from this dispersive regime to the resonance regime, where both spins are placed at the same frequency as the resonator. And here we try to really use this device to study light-matter interactions at the fundamental level. When we look at this in spectroscopy, we see the characteristic vacuum-Rabi splitting between the spin and the photon. We can do so on both sides, also simultaneously. And then in the recent experiments, we try to take this to the time domain, where we should be able to observe vacuum-Rabi oscillations where energy is swapped back and forth between spin and photon. So to do so, the sequence looked quite similar, where we first excite the spin, then turn on the interaction for some time, and finally do dispersive readout of the spin using the resonator. And what we indeed see is that the spin excitation, the spin-up probability oscillates also at a frequency that's consistent with our results from spectroscopy. So yeah, basically the frequency matches the spin-photon coupling strength we see. Okay, as a next step, we then use this on both sides to realize a spin-state transfer. So where we excite a spin excitation on one side, then perform sequential vacuum-Rabi oscillations to finally perform readout on the spin on the other side. And we can see that indeed, for some combinations of interactions times, we indeed transfer the spin excitation to the other side. And then in a final experiment, we wanted to see if we could probe higher states in the Jaynes-Cummings ladder. And to do so, we then excited first both spins and then used one of them to populate the resonator with one photon to then perform a vacuum-Rabi oscillation on the other side. And what you would then expect to see is a square root of 2 speed up in your oscillation. And looking at the data, we indeed see some speed up in the first period, but after that, the oscillation dies out quite quickly. And comparing this to some master equation simulations we did, this seems to indicate that we have some source of stronger photon decay in this experiment. Yeah, we're still looking into it, but we think it might be due to a 2-photon decay process that involves the charge qubit. And with that, I would like to summarize. So we've shown long-range interactions between 2 spin qubits mediated by a resonator, on-chip superconducting resonator. We've done so both in the dispersive regime, where we've shown these 2-qubit I-swap oscillations between spins mediated by virtual photons, and then also in the resonant regime, where we've used vacuum-Rabi oscillations to achieve this spin-state transfer. And these experiments were really enabled by the cooperativity that was reached in our system. And this compares kind of the spin-photon coupling strength to the spin and photon loss rates. And then looking to the future, I think there are several ways we could still improve on this. So first of all, to reduce the spin or improve the spin coherence, we can really improve the charge noise in our system, which also indirectly affects the spin because of our spin-charge hybridization. And in our device, the charge noise was quite severe, also when we compare it to other state-of-the-art silicon spin qubit devices. We can also improve the resonator by optimizing the design for this coupling and also the fabrication process. And finally, we can enhance the coupling strength by going to different materials, also shown by different groups. And then one final thing I would like to mention is that the readout was very challenging in our device, and it would be really useful to have the ability to perform a single-shot readout, either by having a dedicated readout resonator or by including an extra dot to perform readouts based on Pauli spin blockade, which is very common in the spin qubit field. And with that, we think that a 99% resonator-mediated 2-qubit gate between spin qubits should be feasible. And with that, I would like to thank the entire team who contributed to the work, and you all for your attention. Thank you.
Thank you very much. Thanks a lot. So, questions, please. Oh, there's one. Okay, sorry, I didn't see you.
I can.
Well, let's see.
Thank you for your talk. I was wondering if you could talk more about how you intend to deal with the issues of the significant decay you see when you're doing this interaction.
Yeah, sure. Yeah, so I think I think the big issue for us was this charge noise. So in our device, the kind of the charge qubit. Let me see if I have the it's a bit slow. The diagram, but our charge qubit had quite a bad line width of like 60 megahertz, and that's quite a lot worse than for like other devices, for example, measured in our group. So that I think is a big deal, especially when we are in this regime where kind of the spin and charge are maximally hybridized. So I think that's the main thing. And then an open question is, I think, how much of this decay is due to decay through the resonator, but our resonator has a line width of like, let's say, 2.5 megahertz. So I think, working on the charge qubit first would be best.
Okay.
Yeah.
Thanks.
Other question? So I'm also wondering, looking at these type of devices which have so many metallic structures, so there's so many metallic gates, there must be some capacitive loss in the system which cause problem. No.
Yes, indeed. That's actually a very good question. I'll go to the device. It's a bit slow. Okay, I'll just keep clicking while I'm talking. This was indeed also an issue for us. So in earlier devices, we kind of had a loop resonator, and then this decay channel was kind of suppressed. But now with the kind of extended resonator, we indeed saw that when we just fabricate the resonator, the quality factors were okay. But then when we also add these quantum dot gates, we completely lost the resonator, and so that's also work that Patrick Harvey-Collard did, was developing and implementing these filters on the gate lines, and that then kind of recovered or reduced this loss channel through the gates. So it's just an LC filter.
Okay, good. Yeah. Is there anything about the magnet? There's also these magnets on top. Is there noise from the magnets, or is that something we don't have to be worried about?
So not necessarily, I think. No, I think so our biggest source of noise is really the charge. Just charge fluctuators in the environment, and the micromagnets. They just hybridize the spin and the charge.
But there's no spin waves or things like this on the...
Not that I know of.
Okay, good. Okay, then let's thank the speaker once more. Thank you very much. And that closes this session. So thanks for you guys all staying here. And I hand over to Christian.
Great. Thank you, Christian. Great. With that, we are at the end of today's program, and now it's time for going to the dinner, and Amber have some practical information.
Thank you very much. So two subjects, mostly about the dinner tonight, and then also a little bit about the dinner tomorrow. Please don't confuse the two. I will start with the dinner tonight. So it will be a walking dinner from SQA. In the new church. If you have had the chance to visit Delft a little bit, it's at the the market, the central market. You really can't miss it. You might mistake it with the old church, which is even older. So please go to the new church. It starts at 7, so you have an hour to get showered, get dressed up for the gala dinner. At 7, the food compared to previous SQAs will really start from 7 with several courses. It will be a walking dinner, just want to make that clear, so not a seated dinner. Everyone with a badge is welcome, so even if you didn't register, we will have enough space and food for everyone. And the dinner is supported by OrangeQS and IQM, so there will also be some welcome words during the amuse. So that's for tonight, the dinner tonight. Then a hint about the closing party tomorrow. First of all, to make it clear, there is also dinner included there. So if you don't have any dinner plans yet, you could also tomorrow make use of that closing party. It will be at the brewery Koper & Kat, close to Delft Circuits, in the Cable district. And there will be a walk-in between 7 and 8. The closing party is kind of a new element we add to SQA this year, and is supported by local companies, Qblox, Quantware, Delft Circuits, and OrangeQS. And in parallel, actually straight after the conference, the tours at Delft Circuits will start in very close by. So if you want to visit Delft Circuits, make sure that you go straight after the conference closes there, and then you can also afterwards enjoy dinner and drinks. More details on this tomorrow, also more details on the conference picture tomorrow. Yes.
Then see you at dinner.